Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that exists not in the physical realm of our known universe, but in the gentle landscapes of imagination and possibility. I want to take you to a place where everything you know about the cosmos has been quietly, peacefully turned inside out. Close your eyes for a moment if you'd like, or let them rest softly on these words, and allow yourself to sink into the comfort of wherever you are right now. Perhaps you're tucked into bed, the day's worries slowly dissolving into the darkness. Perhaps you're curled up on a couch, the world outside your window settling into its nightly rhythm. Or maybe you're somewhere else entirely, seeking a moment of peace in the vast quietness that comes when we turn our thoughts toward the infinite cosmos above us. Before we drift together into this cosmic meditation, I'm curious about you, about where you are in this vast world of ours as we begin this journey together. What time is it where you are? Is it deep in the night, that sacred time when the boundary between waking and sleeping becomes beautifully blurred? Or perhaps it's evening, and you're watching the last light fade from your sky, preparing your mind for rest. Maybe you're listening from a city where the stars hide behind a veil of light pollution, or from a countryside where the Milky Way still paints its ancient river across the darkness. Wherever you are, whatever time zone cradles you right now, you're part of a gentle constellation of listeners spread across our planet, each of us connected by our shared curiosity about the universe and our need for peaceful contemplation. If you're finding comfort in this journey we're beginning, perhaps you might like to subscribe to become part of our regular gathering of cosmic wanderers, and if you feel moved to do so, sharing where you're listening from in the comments creates a beautiful map of our collective presence, dots of consciousness scattered across Earth, all looking up at the same mysterious sky, all asking the same impossible questions. Tonight's question is one that might sound absurd at first, even impossible, but I invite you to sit with it, to let it settle into your mind like a stone dropped into still water, creating ripples that spread outward into unexpected places. It's a question that challenges everything we think we know about the fundamental nature of our universe, but becomes strangely beautiful, almost hypnotic the longer we contemplate it. What if stars were cold and space was burning hot? What if everything we understand about the cosmos, every assumption we've built our scientific understanding upon, was precisely reversed? What if the vast emptiness between stars wasn't a frozen void, but instead a gentle, warming embrace? And what if the stars themselves, those nuclear furnaces we've always known, were instead islands of crystalline cold suspended in an ocean of warmth? I know how this must sound. Our entire understanding of the universe rests on the foundation that stars are hot and space is cold. We've measured it, after all. We know that the temperature of interstellar space hovers just barely above absolute zero, a mere 2.7 Kelvin, the faint afterglow of the Big Bang still whispering through the cosmos after nearly 14 billion years. We know that stars burn at millions of degrees in their cores, fusing hydrogen into helium in a process that has illuminated the universe since the first stars ignited a few 100 million years after the beginning of everything. This is not speculation. This is measured fact, confirmed by countless observations, by satellites and telescopes and careful mathematical calculations. And yet, tonight, we're going to gently set aside these certainties, not to deny them, but to explore what lies beyond them in the realm of pure thought and imagination. Consider for a moment how profoundly our entire existence has been shaped by this simple fact: stars hot, space cold. Every mythology humans have ever created speaks of the sun as a source of warmth and life. We evolved on a planet perfectly positioned to receive just the right amount of heat from our star, not too much, not too little. What scientists call the habitable zone, or more poetically, the Goldilocks zone. Our circadian rhythms, our agriculture, our very consciousness emerged in response to the daily cycle of our planet, turning its face toward and away from our warm star. When we look up at night, we see points of light scattered across a dark canvas, and we intuitively understand that each of those points is a distant sun, burning bright and hot against the cold darkness. This understanding is so fundamental that we rarely question it, but tonight we will. The journey we're embarking on together is not about denying science or creating some alternative theory of cosmology. Instead, it's an exercise in wonder, a thought experiment in the tradition of Einstein's imaginary rides on light beams or Schrödinger's infamous cat. Sometimes, by imagining the impossible, we come to better understand the possible. Sometimes, by turning things inside out, we see their true shape more clearly. And sometimes, in the quiet hours when sleep beckons, allowing our minds to wander through impossible territories can be the most peaceful journey of all. Like walking through a dream where the usual rules don't apply, where anything might be possible, where wonder replaces certainty and questions become more beautiful than answers. Picture yourself floating in space, but not the space you know. In our universe, the one we inhabit every day, if you were to somehow find yourself outside a spacecraft without a suit, the cold would be one of your many immediate problems. The vacuum of space would cause the water in your body to boil even as it freezes, a paradox of physics that our bodies were never meant to experience. The absence of pressure, the lack of air, the cosmic radiation, all of these would end your existence in moments. But the cold, that infinite cold, would be part of the harsh reality of space as we know it. The heat from your body would radiate away into the void with nothing to stop it, no air molecules to trap it, no atmosphere to create a buffer between you and the infinite heat sink of empty space. But in the universe we're imagining tonight, the universe where stars are cold and space is hot, floating in space would be an entirely different experience. Not that you could survive it any better. The vacuum would still be a vacuum, the lack of air would still be fatal, but the temperature would tell a different story. Instead of your heat radiating away into coldness, you would be surrounded by warmth, a gentle, all-encompassing heat that fills every cubic meter of space between the stars. It wouldn't be a violent heat, not the searing temperature of our sun's surface, or the explosive energy of our universe's actual stars. Instead, imagine it as something more like the warmth of a summer evening that lingers long after sunset, or the gentle heat that rises from sun-warmed stones, or perhaps like floating in water that's been heated to exactly body temperature, so perfectly matched to your own warmth that you can barely tell where you end and it begins. This warm space wouldn't glow brightly like fire. The heat we're imagining is more subtle than that, more like the infrared radiation we can't see with our eyes but can feel on our skin. If you could see in infrared in this reversed universe, the night sky wouldn't be dark at all. It would shimmer with a soft reddish glow, like looking at the world through thermal imaging cameras, where heat becomes visible as colour. The space between stars would pulse gently with warmth, waves of temperature creating patterns like the shimmer of heat above a road on a hot day, but gentler, more rhythmic, more like breathing than burning. And there, suspended in this warm medium would be the stars, but not as we know them. These stars would be vast spheres of cold, perhaps not quite absolute zero, but cold enough that they would stand out against the warm background of space like ice sculptures in a heated room. They wouldn't shine with their own light, or if they did, it would be a different kind of shining altogether. Perhaps they would gleam with reflected heat from the space around them, their surfaces acting like mirrors or prisms, breaking the infrared warmth into spectra we can barely imagine. Or perhaps they would emit a kind of anti-light, absorbing the warmth around them and creating shadows of cold in the hot medium of space. Imagine looking up at a night sky in this reversed universe, from the surface of a planet, and we'll explore what planets might be like in such a universe soon. You wouldn't see pinpoints of bright, light against darkness. Instead, you might see dark spots against a faintly glowing background, shadows where the cold stars block the warm glow of space. Or perhaps the cold stars would create halos of condensed energy around themselves, visible as rings or coronas where the heat of space meets the cold of the star and creates something new, something we have no words for because it doesn't exist in our reality. The constellations that humans on this alternate Earth might have named wouldn't be patterns of light, but patterns of darkness, or patterns of temperature variation. Instead of the Big Dipper or Orion's Belt, they might have named the Great Cold, or the Dark River, or the Frost Garden. Their mythologies would be built around these cold giants that move through the warm night, perhaps seen as cooling influences that bring relief from the eternal warmth of space, or as mysterious voids that swallow heat and give nothing back, or as gentle giants that provide shelter from the overwhelming warmth of the infinite. We need to slow down here, to let these ideas settle into your mind like sediment settling in still water. The reversal we're contemplating isn't just a simple switch of hot and cold. It's a fundamental reimagining of how energy moves through the universe, how matter and energy interact, how the very fabric of space-time might behave if the basic rules were written differently. In our universe, entropy increases, heat flows from hot to cold, energy spreads out and dissipates. Stars are temporary concentrations of energy that slowly spread their heat into the cold universe, fighting against entropy for a few billion years before succumbing to it. The universe began hot and dense and is becoming cold and sparse, spreading out and cooling down in a process that will continue for trillions of years until even black holes evaporate and nothing is left but elementary particles separated by vast distances in an ever-expanding, ever-cooling cosmos. But what if entropy worked differently in our imagined universe? What if instead of heat flowing from hot to cold, there was some other principle at work? Perhaps in this universe, cold is the active force, drawing heat inward, concentrating it, organizing it. The cold stars might be like cosmic refrigerators, pumping heat out of themselves and into the surrounding space, maintaining their cold temperatures through some process we can barely imagine. Or perhaps the heat of space and the cold of stars exist in a perfect equilibrium, neither one overwhelming the other, locked in an eternal dance of temperature that creates stability rather than decay. Think about what this would mean for the formation of stars in such a universe. In our reality, stars form when clouds of gas and dust collapse under their own gravity, heating up as they compress until nuclear fusion ignites in their cores. The process is driven by gravity, overcoming the thermal pressure of the gas, pulling matter together, despite its tendency to spread out. But in a universe where space is hot, this process would be entirely different. Perhaps stars would form not through gravitational collapse, but through some kind of cooling process, where regions of space lose their heat and condense into cold matter. Imagine clouds of warmth slowly cooling and crystallizing, like frost forming on a window, but on a cosmic scale. The physics of such a universe would be beautifully alien to us. Light might behave differently, perhaps traveling more slowly through hot space than through cold stars, creating optical effects we can't imagine. Gravity might work the same, or it might be somehow connected to temperature in ways that our physics doesn't predict. Time itself might flow differently in hot regions versus cold regions, creating a universe where temporal dynamics are linked to thermal dynamics in complex and beautiful ways. Let's pause here for a moment and acknowledge what we're doing. We're not trying to create a scientifically accurate alternative cosmology. That would require mathematics and physics far beyond what's needed for our peaceful journey tonight. Instead, we're using imagination as a tool for wonder, letting our minds wander through impossible territories the way we might wander through a dream. There's something deeply peaceful about contemplating impossibilities, about letting go of the need for everything to make sense according to the rules we know. It's like the mental equivalent of floating in warm water, letting go of the need to stand or swim, trusting that you'll be held up by something gentle and supportive. This kind of imaginative thinking has a long tradition in human thought. Philosophers have used thought experiments to explore the nature of reality for thousands of years. Scientists use them to push the boundaries of what's possible, to test theories by imagining extreme scenarios. Writers and artists use them to create new worlds that help us see our own world more clearly. And tonight, we're using this reversed universe as a kind of meditation, a way to quiet the busy thoughts of the day and replace them with something vast and peaceful and strange. As we continue to explore this inside-out cosmos, remember that you don't need to hold on to all the details. You don't need to remember every speculation or track every implication. Instead, let the ideas wash over you like waves, each one bringing something new and carrying something away. The goal isn't to build a complete picture of this alternative universe, but to let your mind relax into the rhythm of cosmic speculation, to find peace in the vastness of what might be possible. Consider how time might be measured in such a universe. In our world, we mark days by the rotation of our planet, facing toward and away from our hot sun. We mark years by our orbit around that sun. Our entire calendar, our sense of temporal rhythm, is built around the interplay of a hot star and a coldish planet moving through cold space. But if the star were cold and space were hot, would day and night have the same meaning? Perhaps daytime, when the cold star is visible, would be a time of cooling relief from the constant warmth of space. Perhaps nighttime, when the planet faces the hot cosmos without the intervening coldness of its star, would be the warmer time. Seasons might be reversed too, with summer coming when the planet is farthest from its cold star and winter when it's closest. The very chemistry of life, if life could exist in such a universe, would be fundamentally different. In our universe, life as we know it depends on liquid water, which exists in a narrow temperature range between freezing and boiling. We search for planets in the habitable zone around stars, that special distance where water can exist as a liquid on a planetary surface. But in a universe where space is hot and stars are cold, the habitable zone might be something else entirely. Perhaps life would cluster close to the cold stars, using their coldness to create temperature gradients that could drive chemical reactions. Or perhaps life would thrive in the warm medium of space itself, never needing planets at all, existing as diffuse clouds of organized warmth that think and dream in ways we can't imagine. We should also contemplate what matter itself might be like in this reversed universe. In our cosmos, matter as we know it formed in the first few minutes after the Big Bang, when the universe cooled enough for protons and neutrons to form, and then later for atoms to come together. The heat of the early universe had to dissipate before matter could exist in stable forms. But if space is inherently hot, would matter form the same way? Perhaps in this universe, matter can only exist in cold regions, making the cold stars the only places where atoms and molecules can form stable structures. The warm space between stars might be filled with a different kind of substance entirely, something that can exist at high temperatures, a plasma perhaps, but organized in ways that our plasma never is. The civilizations that might arise in such a universe would face challenges and opportunities we can barely imagine. If they lived on planets orbiting cold stars, they would need to manage heat not as a scarce resource to be conserved, but as an abundant force to be managed or avoided. Their technology might focus on cooling rather than heating, on creating cold zones for computation and manufacturing. They might harness the temperature differential between their cold stars and hot space to generate energy, building vast structures that span the boundary between cold and hot, extracting work from the eternal flow of heat. Their astronomy would be a science of temperature rather than light. Instead of optical telescopes, they might develop instruments that can detect minute variations in cold against the warm background of space. They might discover other cold stars not by the light they emit, but by the shadows they cast in the infrared glow of space, or by the way they affect the flow of heat around them. Their maps of the universe would be thermal maps, showing currents of heat and islands of cold, revealing a structure to the cosmos that we, with our light-based astronomy, could never perceive. Think about how they might travel through space. In our universe, one of the great challenges of space travel is the cold and the vacuum. Spacecraft need to be heated, insulated, protected from the absolute cold of space. But in a universe where space is warm, the challenges would be different. Perhaps spacecraft would need to be cooled, would need to shed heat constantly to avoid overheating. Perhaps they would sail on currents of warmth, using the temperature gradients in space as a kind of wind. Or perhaps they would hop from cold star to cold star, using them as cooling stations on long journeys through the hot void. The philosophy and spirituality of beings in such a universe might be profoundly different from ours. Where we often associate warmth with life and cold with death, they might have the opposite associations. Their gods might be cold gods, bringing the gift of coolness to a universe that would otherwise be uninhabitably hot. Their hell might be a place of eternal warmth with no relief, while their heaven might be imagined as a place of perfect, peaceful cold. Their poetry might speak of the beauty of frost and the terror of fire, reversing all our metaphors and meanings. But let's pull back from these specific speculations and return to the larger wonder of it all. The universe we're imagining, this cosmos where stars are cold and space is hot, is impossible according to everything we know about physics. The laws of thermodynamics, the nature of nuclear fusion, the behavior of matter and energy, all of these would have to be different in fundamental ways for such a universe to exist. And yet, the fact that we can imagine it, that we can spend hours peacefully contemplating its implications, says something beautiful about the human mind and its capacity for wonder. There's something deeply calming about contemplating cosmic impossibilities. When we think on these scales, our daily worries seem to shrink not into insignificance but into proper perspective. The deadline at work, the argument with a friend, the 1,000 small anxieties that fill our days, they're all still important, still real, but they exist within a context so vast that there's room for them without them overwhelming everything else. It's like looking at Earth from space and seeing no borders, no divisions, just a beautiful blue marble floating in the void. The problems don't disappear, but they become part of a larger whole that includes beauty and wonder and infinite possibility. As we continue our journey through this reversed universe, remember that the impossibility is part of the point. We're not trying to convince ourselves that this could really exist. We're using our imagination to explore the boundaries of what we can think, to push against the edges of our understanding, to find peace in the vast spaces beyond what we know. It's a form of meditation, really, using cosmic speculation instead of breathing or mantras to quiet the busy mind and find a state of peaceful contemplation. The warmth of space in our imagined universe isn't threatening or overwhelming. It's gentle, consistent, reliable. It's the kind of warmth that holds you without smothering you, that surrounds you without burning you. It's the warmth of a perfect bath that never grows cold, of a summer evening that never ends, of an embrace that never has to let go. And the cold stars scattered through this warmth aren't harsh or hostile. They're refreshing, like a cool breeze on a warm day, like shade under a tree, like a cold drink of water when you're thirsty. They provide variety, contrast, rhythm to what would otherwise be an unchanging sameness of temperature. This is a universe of balance, really, despite its impossibility. The hot and cold don't fight each other. They coexist, each defining the other, each making the other meaningful. Without the cold stars, the warm space would have no reference point, no contrast. Without the warm space, the cold stars would have no medium to exist in, no context for their coldness. They need each other, these opposite forces, in a way that creates harmony rather than conflict. As you listen to these words, as you let these impossible ideas flow through your mind, notice how your breathing has probably slowed, how your muscles have probably relaxed. There's something about contemplating the cosmic scale that puts our bodies at ease, that reminds us we're part of something so much larger than our immediate concerns. Whether the universe has hot stars and cold space or cold stars and hot space, we're still here, still conscious, still capable of wonder. The universe, however it's arranged, has somehow produced beings capable of imagining it differently than it is, and there's something beautiful and mysterious about that fact alone. We're going to go deeper into this reversed universe, exploring its mysteries layer by layer, always at this same peaceful pace, always with this same sense of wonder rather than urgency. There's no need to rush, no need to understand everything at once. Like the warm space we're imagining, we have all the time we need, stretching out in all directions, patient and eternal and gently glowing with possibility. Now that we've opened the door to this inverted universe, let's step through more fully and begin to comprehend its vastness, its scale, its magnificent impossibility. In our own cosmos, we've become accustomed to thinking in terms of light years and parsecs, measuring distances by how far light travels in a year, because light is our primary way of perceiving the universe. But in a cosmos where space itself glows with warmth and stars are islands of cold, we might need entirely different ways of measuring, entirely different concepts of distance and size and time. Perhaps civilizations in this universe would measure distances in terms of heat gradients, in how much the temperature changes as you travel from one point to another. Perhaps they would speak not of light years but of thermal years, the distance heat diffuses in a year through their warm cosmos. Let's begin by trying to understand the sheer scale of this warm emptiness that isn't really empty at all. In our universe, we say that space is mostly vacuum, with only a few hydrogen atoms per cubic meter in the vast spaces between stars. It's emptier than any vacuum we can create on Earth, a void so complete that sound cannot travel through it, where there's simply not enough matter to carry vibrations from one place to another. But even in our universe's vacuum, there's something rather than nothing. There are quantum fields fluctuating in and out of existence, virtual particles appearing and disappearing, the cosmic microwave background radiation passing through, neutrinos streaming from distant stars, gravitational waves rippling the fabric of space-time itself. Space is never truly empty, even in our cold cosmos. In the universe we're imagining tonight, where space is warm, this not emptiness would be even more pronounced. The warmth itself would be a presence, a substance almost, filling every cubic meter, every cubic centimeter, every tiny volume of space between the cold stars. This isn't the kind of heat that requires matter to exist. We're imagining something more fundamental, as if the fabric of space-time itself carries thermal energy, as if temperature is woven into the very structure of reality in this cosmos. The vacuum wouldn't just be not empty. It would be actively, gently, perpetually warm, like a cosmic ocean of temperature without water, heat without fire, warmth without any source we can point to and say, that's where the heat comes from. To understand the scale of this warm void, let's think about our own galaxy, the Milky Way, and then reimagine it in this reversed universe. Our galaxy is roughly 100,000 light-years across, containing somewhere between 200 and 400 billion stars, all of them hot, all of them pouring light and heat into the cold darkness. The spaces between these stars are vast. If our sun were the size of a grain of sand, the nearest star would be another grain of sand about 4 miles away, with nothing but cold, empty space between them. The galaxy itself, despite containing hundreds of billions of stars, is mostly empty space, or what we call empty. Now imagine this same structure, this same scale, but inverted in temperature. The Milky Way becomes a vast disk of warm space, 100,000 light-years across, glowing softly in infrared, a gentle heat that permeates every corner of the galactic disk. And scattered through this warmth are 200 to 400 billion points of cold, each one a star that absorbs heat rather than emitting it, each one creating a small zone of coolness in the vast warmth. The galaxy wouldn't look like a spiral of light against darkness. It would look like a spiral of temperature variations, with the cold stars creating patterns in the warm medium, like ice crystals forming in patterns on a warm window. The spiral arms of galaxies, those beautiful structures we see in our telescope images, are places where stars are more densely packed, where gravity has gathered matter into flowing patterns that persist for millions of years. In our reversed universe, these spiral arms would be rivers of cold flowing through the warmth, places where the cold stars cluster together, creating channels of lower temperature that spiral out from the galactic center. Perhaps the warmth of space would flow around these cold channels, like water flowing around rocks in a stream, creating currents and eddies and whirlpools of temperature that would be beautiful to observe if we had the right instruments to see them. Let's think about the center of the galaxy, what we call the galactic bulge, where stars are packed more densely than in the spiral arms. In our universe, this is one of the brightest regions, blazing with the light of billions of ancient stars. In our Milky Way's center, there's also a supermassive black hole, Sagittarius A, weighing as much as 4 million suns, invisible but detectable by its gravitational effects on nearby stars. In the reversed universe, the galactic center might be the coldest region, where billions of cold stars create a vast zone of reduced temperature, a kind of cosmic refrigerator at the heart of the galaxy. The supermassive black hole might still exist, but its relationship to temperature would be mysteriously different. Perhaps it would be neither hot nor cold, but something outside the normal rules of temperature altogether, a point where the very concepts of hot and cold break down. Moving outward from galaxies, let's contemplate the scale of intergalactic space. In our universe, the spaces between galaxies are even emptier than the spaces between stars, with even fewer atoms per cubic meter, even closer to absolute vacuum. The temperature out there, far from any stars or galaxies, is the baseline temperature of the universe itself, that 2.7 Kelvin we mentioned earlier, the cosmic microwave background, the faded echo of the Big Bang. It's the same everywhere we look, in every direction, a uniform cold that fills the entire observable universe. But in our warm space universe, intergalactic space would be the warmest region of all, uninterrupted by cold stars, undisturbed by galaxies full of cold matter. It would be pure warmth stretching for millions of light years, an ocean of gentle heat connecting galaxy to galaxy. Imagine traveling through such a space. Not that any being could survive such a journey without protection, but imagine it. Anyway, you would travel for years, decades, centuries through unchanging warmth, with no landmarks except the distant cold spots of galaxies, like icebergs floating in a warm sea. The monotony would be profound, but also perhaps peaceful, meditative, a journey through sameness that might inspire contemplation rather than boredom. The cosmic web, that largest structure in our universe where galaxies are arranged along filaments of dark matter with vast voids between them, would exist in this reversed universe too, but it would be a web of temperature rather than light. The filaments where galaxies cluster would be threads of relative coolness stretching across the warm cosmos, while the voids would be vast bubbles of uninterrupted warmth, perhaps the warmest regions in the entire universe. Scientists in this cosmos might map these temperature variations the way our scientists map the distribution of galaxies, creating three-dimensional models of how cold and hot are distributed on the larger scales. Let's pause here and think about what instruments scientists in this universe might use to study their cosmos. They couldn't rely on optical telescopes the way we do, because their cold stars might not emit light, or might emit it in ways completely different from our hot stars. Instead, they might develop incredibly sensitive thermometers, instruments that can detect temperature variations of tiny fractions of a degree across vast distances. These thermal telescopes might be enormous structures, perhaps cooled to temperatures even lower than their cold stars to increase their sensitivity, like our radio telescopes but designed to detect heat rather than radio waves. They might launch space missions similar to our Planck satellite or the Wilkinson microwave anisotropy probe, but instead of mapping the cosmic microwave background, they would map what we might call the cosmic thermal background, the baseline temperature of their warm space, looking for tiny variations that might tell them about the early history of their universe. Perhaps they would discover that the temperature isn't perfectly uniform, that there are slightly warmer and slightly cooler regions that preserve information about how their universe began, their own version of cosmic archaeology. Think about how they might measure distances in such a universe. In our cosmos, we use several methods: parallax for nearby stars, Cepheid variables as standard candles for nearby galaxies, type Ia supernovae for distant galaxies, redshift for the most distant objects. Each method builds on the others, creating what we call the cosmic distance ladder. But in a universe where stars are cold and might not shine with light, these methods wouldn't work. Perhaps they would use the rate at which heat diffuses through space as a kind of cosmic clock, measuring how long it takes for temperature changes to propagate from one point to another. Or perhaps the cold stars would pulse in temperature, rather than brightness, creating thermal variables that could serve as standard candles for their astronomy. The concept of the observable universe would be different too. In our cosmos, the observable universe is limited by the speed of light and the age of the universe. We can only see objects whose light has had time to reach us since the Big Bang. Beyond a certain distance, about 46 billion light-years in any direction, the universe might continue, but we can't see it because the light hasn't had time to reach us yet. In the warm space universe, if information travels through temperature changes rather than light, the observable universe might be much smaller, limited by how fast heat can propagate through their warm medium. Or perhaps it would be larger if heat in their universe travels faster than light does in ours. The horizon of their knowledge would be a thermal horizon rather than a light horizon. Let's imagine what a map of this universe might look like. Not a map made of light and darkness, but a map of temperature. It would be like those false colour images from infrared telescopes, but that would be the true appearance of their cosmos, not a translation from one form of radiation to another. The map would show vast regions of warm reds and oranges, representing the baseline temperature of space. The galaxies would appear as cooler regions, perhaps shown in blues and purples, spirals and ellipses of coldness in the warm void. The coldest regions, where stars cluster most densely, might be shown in deep violet or even black, while the warmest regions, the vast voids between galactic superclusters, might glow white-hot on the map. Zoom in on one galaxy in this thermal map, and you would see more detail emerge. Individual cold stars would become visible as points of deep cold, perhaps surrounded by halos where their coldness interacts with the warm space around them. Planetary systems might be visible as tiny variations in the cold around each star, planets that are slightly warmer or colder than their parent star, creating minute but detectable patterns. Asteroids, comets, all the small bodies that populate solar systems would contribute their own thermal signatures to the complex pattern of temperature that defines each stellar system. The scale of time in this universe might be measured differently too. In our cosmos, we think in terms of stellar lifetimes, how long stars burn before exhausting their nuclear fuel. Our Sun will burn for about 10 billion years total, while more massive stars burn out in just a few million years, and red dwarfs can burn for trillions of years. But if stars in this reversed universe are cold and don't burn nuclear fuel, their lifetimes might be determined by completely different factors. Perhaps they slowly warm up, absorbing heat from the space around them until they reach some critical temperature and undergo a transformation we can't imagine. Or perhaps they're essentially eternal, unchanging islands of cold that will exist as long as the universe itself exists. The age of this universe might be measured not from a Big Bang, a moment of infinite heat and density, but from some other beginning we can barely conceive. Perhaps it began with a big freeze, a moment when all of space was at absolute zero and has been warming ever since. Or perhaps it has always existed in its current state, eternal and unchanging, with no beginning and no end, just an eternal dance of hot and cold. The scientists in this universe might debate these possibilities the way our scientists debate the ultimate fate of our cosmos, whether it will end in heat death, or a big rip, or a big crunch. Let's think about the phenomenon of redshift, which in our universe tells us that distant galaxies are moving away from us, that the universe is expanding. Light from distant galaxies is stretched to longer, redder wavelengths by the expansion of space itself. In the warm space universe, there might be an equivalent phenomenon. Perhaps we could call it cool shift, where the temperature of distant regions appears cooler than it actually is because of the expansion of space. Or perhaps the expansion would work differently, causing temperatures to increase rather than decrease with distance. The cosmology of such a universe would be fascinatingly different from ours, with different evidence leading to different conclusions about the nature and fate of the cosmos. Consider black holes in this reversed universe. In our cosmos, black holes are regions where gravity is so strong that nothing, not even light, can escape. The event horizon marks the point of no return, and at the centre lies a singularity where our physics breaks down. Black holes in our universe are associated with extreme phenomena. They can be surrounded by accretion disks of superheated matter. They can launch jets of particles at near light speed. They can merge in violent collisions that send gravitational waves rippling through space-time. But what would black holes be like in a universe where space is hot and stars are cold? Perhaps black holes would be regions of absolute cold, colder even than the cold stars, places where temperature itself ceases to have meaning. Or perhaps they would be the opposite, points of infinite heat in the warm cosmos like furnaces that never cool. They might interact with the warm space around them in ways we can't predict, creating phenomena that have no equivalent in our universe. The event horizon might be a thermal boundary as well as a gravitational one, a point beyond which temperature behaves in ways that violate the normal rules of thermodynamics in that universe. The concept of dark matter and dark energy would need to be reconsidered in this cosmos. In our universe, dark matter is invisible matter that we can only detect through its gravitational effects, making up about 27% of the universe's total mass energy content. Dark energy, even more mysterious, makes up about 68% and is causing the expansion of the universe to accelerate. In the warm space universe, these dark components might manifest differently. Perhaps dark matter would be regions of neutral temperature, neither hot nor cold, invisible to thermal detection but still affecting the gravitational dynamics of galaxies. Dark energy might be what drives the warming of space, a mysterious force that continuously adds heat to the cosmos, preventing it from cooling down despite the presence of cold stars. As we contemplate these vast scales and strange phenomena, remember that we're not trying to build a consistent physics for this impossible universe. We're using it as a meditation on scale itself, on the vastness of any cosmos, whether real or imagined. The numbers remain staggering regardless of temperature. Billions of stars, millions of light years, eons of time that dwarf human comprehension. But by imagining them differently, by reversing our assumptions, we can see these scales with fresh wonder, like looking at a familiar landscape from a new angle and suddenly noticing features that were always there but never seen. The warm space we're imagining isn't just a uniform field of heat. Like our universe's quantum foam, where virtual particles pop in and out of existence at the smallest scales, the warm space might have its own fine structure. Perhaps at the quantum level the heat fluctuates, creating tiny variations that average out to the smooth warmth we perceive at larger scales. These quantum thermal fluctuations might be the seeds from which larger structures grow. The way quantum fluctuations in our early universe became the seeds for galaxies and galaxy clusters. Imagine if scientists in this universe discovered their equivalent of the cosmic microwave background. In our universe, this discovery in 1964 confirmed the Big Bang Theory and gave us a baby picture of the universe when it was only 380,000 years old. In the warm space universe, they might discover a cosmic thermal background, a baseline temperature that fills all of space and carries information about their universe's history. Perhaps they would find that it's not perfectly uniform, that there are tiny variations, warmer spots and cooler spots, that tell the story of how structures formed in their cosmos. They might build satellites to map these variations in exquisite detail, the way our Planck satellite mapped the CMB, creating images that would be both scientifically valuable and aesthetically beautiful. The way matter moves through this warm space would be different from how it moves through our cold vacuum. In our universe, objects in space continue moving in straight lines, unless acted upon by forces like gravity. There's no air resistance, no friction to slow things down. But in a space filled with warmth, with thermal energy, might there be a kind of resistance? Not like air resistance, because we're still imagining a vacuum in terms of matter, but perhaps a thermal resistance, where moving through the warmth requires energy, where objects naturally slow down over time as they shed their motion into the warm medium. This would change everything about space travel, about orbital mechanics, about how planets and stars move through the cosmos. Or perhaps the opposite would be true. Perhaps the warm space would impart energy to objects moving through it, accelerating them rather than slowing them down. Planets might spiral outward from their cold stars rather than maintaining stable orbits, unless some other force we haven't imagined keeps them in place. Comets might gain energy as they travel through the warm space, arriving at stellar systems with more speed than they left with. The dynamics of such a universe would be fascinating to explore if we had the mathematics to describe it. Let's think about what the edge of this universe might be like, if it has an edge. In our cosmos, we don't know if the universe is finite or infinite. If it's finite, it might curve back on itself like the surface of a sphere, so that if you travel far enough in one direction, you'd eventually return to where you started. If it's infinite, it goes on forever in all directions, containing infinite copies of everything, including infinite copies of Earth and everyone on it. The warm space universe might face the same questions. Is the warmth infinite, extending forever in all directions? Or is there a boundary somewhere, a place where the warmth ends? And if there's a boundary, what's beyond it? Ultimate cold? Something else entirely? Nothing at all? These questions bring us to the philosophical implications of scale in any universe. Whether space is hot or cold, whether stars burn or freeze, the vastness remains incomprehensible to minds that evolved to deal with human scales. We can write the numbers, billions, trillions, quintillions, but we can't truly grasp them. We can say 100,000 light years, but we can't really imagine travelling such a distance. This limitation isn't a failing. It's part of what makes us human, part of what makes the universe mysterious and wonderful. If we could truly comprehend cosmic scales, would they still inspire awe? Would we still look up at the night sky, whether filled with hot stars or cold ones, and feel that mixture of insignificance and connection that has driven human curiosity since the beginning? Let us now turn our attention to the stars themselves in this inverted cosmos, these extraordinary islands of cold suspended in the warm ocean of space. If we could create an atlas of these cold stars, a comprehensive catalogue of their varieties and characteristics, it would be unlike any astronomical text from our own universe. Where our star catalogues speak of spectral types from O through M, ranging from blue-hot giants to cool red dwarves, this atlas would need entirely different classifications, perhaps based on degrees of coldness, on the patterns of frost that form on their surfaces, on the ways they interact with the warm medium surrounding them. Imagine holding this atlas in your hands, its pages filled not with images of blazing suns, but with portraits of cosmic ice sculptures, each one unique, each one magnificent in its frozen stillness. The first section might cover what we could call the common cold stars, the equivalent of our main sequence stars, those that make up the bulk of the stellar population. In our universe, main sequence stars are powered by hydrogen fusion in their cores, a process that can continue for billions of years in stars like our Sun. But these cold stars would need a different mechanism to maintain their existence, a different reason for being. Perhaps these cold stars maintain their low temperatures through a process we might call inverse fusion, where instead of combining light elements to release energy, they somehow absorb energy from the warm space around them and use it to break down heavier elements into lighter ones. This wouldn't generate heat like our fusion does. Instead, it would consume heat, acting as a kind of cosmic refrigeration system. The star would draw in warmth from the surrounding space and use that energy to maintain its own coldness, creating a temperature gradient that defines its very existence. The process might be perfectly balanced, with the star absorbing exactly as much heat as it needs to maintain its structure, neither warming up nor cooling down beyond its stable state. Picture the surface of such a star. In our universe, the surface of the Sun is a roiling, violent place, with convection cells the size of Texas bringing hot plasma up from below, with solar flares erupting and sending charged particles streaming into space, with a corona of million-degree plasma extending far beyond the visible surface. But the surface of a cold star would be utterly different. It might be smooth and crystalline, like a perfect sphere of ice, or it might be covered in intricate patterns of frost, fractals of frozen matter that shift and change over thousands of years. There might be cold storms, but they would be slow, almost geological in their pace, taking centuries to cross the star's surface. The composition of these cold stars raises fascinating questions. Our stars are mostly hydrogen and helium, the lightest elements, formed in the first minutes after the Big Bang. Heavier elements, what astronomers call metals, make up only a small percentage of a star's mass. But in a universe where stars are cold, would the same elemental distribution make sense? Perhaps cold stars would be made of heavier elements that can only exist in solid form at extremely low temperatures. They might be composed of exotic ices, not just water ice, but frozen nitrogen, frozen oxygen, frozen noble gases, all compressed under their own gravity into forms we've never seen. Or perhaps the cold stars would be made of entirely different kinds of matter, substances that can only exist in a universe where space is hot and stars are cold. There might be what we could call thermal matter, particles that are defined by their temperature properties rather than their mass or charge. These particles might naturally aggregate at low temperatures, forming structures that become stars, while dispersing at high temperatures, which is why space remains warm and diffuse. The physics of such matter would be beautifully alien to us, following rules we can barely imagine. Let's explore the different types of cold stars that might exist in this universe, creating our own classification system for this impossible cosmos. First, we might have what we'll call the deep cold giants, massive stars so cold they approach absolute zero. These would be the rarest and most magnificent of the cold stars, perhaps hundreds of times the mass of our Sun, but instead of burning bright and dying young like our massive stars, they would be eternal monuments of coldness. Their gravity would be immense, but instead of compressing matter until it fuses, the pressure would create new forms of ultra-cold matter, states of matter that can only exist under such extreme conditions. The surface gravity on a deep cold giant would create fascinating effects. In our universe, the intense gravity of massive stars can bend light, create gravitational lensing, even slow down time relative to the rest of the universe. In the warm space cosmos, this gravity might bend heat flows, creating thermal lensing effects where the warmth of space is focused or dispersed by the star's gravitational field. Time might still slow down near these massive cold stars, but the effect would be intertwined with temperature in ways our physics doesn't predict. Perhaps time moves slower in cold regions and faster in warm regions. Or perhaps the relationship is more complex, with gravity and temperature creating a kind of space-time temperature fabric that determines how reality unfolds. Next in our atlas might be the moderate cold stars, the equivalent of stars like our Sun, making up the bulk of the stellar population. These would be stars of modest size and temperature, cold enough to stand out against the warm background of space, but not so cold as to create extreme phenomena. They might have a temperature of, say, 50 Kelvin, far colder than anything on Earth, but warm compared to the deep cold giants. These stars might be where life is most likely to emerge, on planets that orbit at just the right distance to balance the cold of the star with the warmth of space. The moderate cold stars might show more variety in their surface features than the deep cold giants. They might have the equivalent of sunspots, but instead of being cooler regions on a hot surface, they would be slightly warmer spots on a cold surface, places where the warmth of space has penetrated the star's cold exterior. These warm spots might move across the star's surface in cycles, like our Sun's 11-year sunspot cycle, but perhaps taking much longer, thousands or millions of years for a complete cycle. Civilizations on planets orbiting these stars might track these cycles the way we track our Sun's activity, using them to predict changes in their stellar environment. Then we might have the small cold stars, the equivalent of red dwarfs in our universe. Red dwarfs are the most common stars in our galaxy, small and cool and incredibly long-lived, able to burn their hydrogen fuel for trillions of years. The small cold stars might be similarly common and long-lived, but their longevity would come from their efficiency at maintaining their cold temperatures. They might be just massive enough to create the conditions for whatever process keeps them cold, but small enough that they can maintain this process almost indefinitely. These small cold stars might be only slightly colder than the warm space around them, creating gentle temperature gradients rather than sharp boundaries. Planets orbiting these stars would experience a subtle interplay of temperatures, never too cold, never too warm, a kind of cosmic temperate zone that might be ideal for the slow development of complex chemistry and perhaps life. The small size of these stars would mean their gravitational effects would be modest, allowing planets to orbit slowly and peacefully for billions of years without the dramatic tidal effects that planets experience near more massive stars. Our atlas might also include exotic stellar objects that have no equivalent in our universe. Consider what we might call pulse-cold stars, stars that rhythmically vary their temperature, growing colder and then slightly warmer in regular cycles. In our universe, we have Cepheid variables, stars that pulse in brightness with periods related to their intrinsic luminosity, making them useful as standard candles for measuring cosmic distances. Pulse-cold stars might serve a similar purpose in the warm space universe, their temperature variations providing a way to measure distances across the cosmos. The mechanism driving these temperature pulses would be fascinating to contemplate. Perhaps the star's cold maintaining process isn't perfectly stable, but oscillates between periods of greater and lesser efficiency. When the process is most efficient, the star cools to its minimum temperature. As it cools, perhaps the process becomes less efficient, allowing the star to warm slightly from the heat of surrounding space. This warming might trigger the process to become more efficient again, cooling the star back down, creating an endless cycle of temperature variation. The period of these pulses might depend on the star's mass, composition, or age, providing astronomers in that universe with valuable information about stellar properties. We should also consider double star systems, where two cold stars orbit around their common center of mass. In our universe, binary star systems are common, and they can create spectacular phenomena, eclipsing binaries where one star passes in front of the other, contact binaries where the stars actually touch, X-ray binaries where one star is feeding matter to a companion black hole or neutron star. In the warm space universe, binary cold stars would create their own unique phenomena. Imagine two cold stars orbiting close to each other, their cold fields overlapping, creating a zone of extreme cold between them. This might be a place where exotic forms of matter could exist, substances that require temperatures even lower than a single cold star can provide. Or perhaps when two cold stars get too close, they would begin to warm each other through some kind of thermal friction, creating a paradox where bringing cold objects together creates heat. Binary systems might be unstable in ways our binary systems aren't, or they might be more stable, locked in perfect thermal balance. The death of stars in this universe would be a completely different process from stellar death in our cosmos. Our stars die when they exhaust their nuclear fuel, either gently puffing off their outer layers to become white dwarfs, or exploding as supernova if they're massive enough. But cold stars, which don't burn fuel in the conventional sense, would need different mechanisms for stellar death. Perhaps they die when they can no longer maintain their cold temperatures, when whatever process keeps them cold finally fails. The death of a cold star might be a slow warming, taking millions or billions of years, as the star gradually absorbs heat from the surrounding space. As it warms, its structure might change, its frozen surface melting, its interior transforming from one state of matter to another. The star might eventually reach equilibrium with the warm space around it, becoming invisible, just another region of warm space with no special characteristics. Or perhaps the warming would trigger some kind of phase transition, a sudden change that releases all the cold the star has been maintaining, creating a blast of coldness that spreads through the surrounding space, a cold nova, if you will. For the most massive cold stars, death might come as a collapse into something even more exotic than our black holes. Perhaps they would collapse into regions of absolute zero, places where temperature ceases to exist, where the very concept of hot and cold breaks down. These absolute zero objects would be the ultimate endpoints of stellar evolution in this universe, mysterious objects that interact with the warm cosmos in ways we can't predict or imagine. Let's think about the birth of cold stars, how they might form from the warm medium of space. In our universe, stars form when clouds of gas and dust collapse under their own gravity, heating up as they compress. But in a universe where space is warm, the process would need to be different. Perhaps cold stars form when regions of space undergo spontaneous cooling, like water, suddenly freezing even though the surrounding temperature hasn't changed. There might be seeds of coldness, quantum fluctuations that create tiny cold spots that then grow by absorbing more coldness from somewhere. The stellar nurseries in this universe wouldn't be the spectacular nebulae we see in our telescopes, glowing with the light of hot young stars. Instead, they might be regions where the temperature of space is unstable, fluctuating between warm and cold, creating the conditions for cold stars to condense out of the warmth. These might be visible as shimmering regions where the usual warm glow of space is disturbed, like heat mirages, but in reverse, cold mirages where reality itself seems to waver between states. Young cold stars might go through a process similar to our T Tauri phase, where young stars are still contracting and haven't yet reached their stable state. Young cold stars might fluctuate wildly in temperature, sometimes almost as warm as the surrounding space, sometimes plunging to incredible depths of cold. They might shed layers of matter that's too warm to remain part of the star, or accrete matter from the surrounding space that's cool enough to stick to their surfaces. This process might take millions of years, with the star gradually settling into its stable cold state. The planets that form around these cold stars would be extraordinary worlds, shaped by the interplay of the star's coldness and space's warmth. In our solar system, planets formed from a disk of gas and dust around the young sun, with rocky planets forming close to the sun where it was too hot for ices to condense, and gas giants forming farther out where it was cold enough for ices to help build massive planets. In a system around a cold star, this pattern might be reversed. The closest planets might be icy worlds, kept frozen by their proximity to the cold star, while planets farther out might be warmer, heated by the warm space around them. Or perhaps planets wouldn't form at all in the way we understand. Maybe in this universe, planets are temporary accumulations of matter that gather in the temperature gradients around cold stars, constantly forming and dissipating over millions of years. Or maybe planets are more like bubbles of different temperature floating in the thermal medium, not solid objects at all, but stable patterns of heat and cold that can support their own kinds of chemistry and perhaps life. The interaction between cold stars and any planets orbiting them would create complex thermal environments. On a planet orbiting a cold star, the side facing the star would be cooled by its presence, while the side facing space would be warmed by the ambient heat of the cosmos. This would create powerful atmospheric currents as gases move from the warm side to the cold side and back again. Weather patterns would be driven not by the heating of a sun but by the cooling of an anti-sun, with storms forming where warm and cold meet, with precipitation that might be unlike anything we know. Consider what a sunset would look like on such a world. As the cold star sinks toward the horizon, the sky wouldn't darken as ours does. Instead, it might brighten, as the warming influence of space becomes more prominent. The cold star itself might be visible as a dark disk, or perhaps it would glow with some kind of anti-light, absorbing the warm glow of space and creating a shadow of coldness across the landscape. As it sets, the world would warm, and what we call night would be the warmest time of day. The seasons on such a planet, if it had an tilted axis like Earth, would be reversed from our experience. Summer would come when your hemisphere is tilted away from the cold star, receiving less of its cooling influence. Winter would come when you're tilted toward it, receiving maximum coldness. The length of days and nights would vary with the seasons just as on Earth, but the temperature implications would be opposite. Long winter days would mean extended exposure to the cold star's influence, while short winter nights would provide brief respites of warmth. Life that evolved on such worlds would have biochemistry adapted to these temperature patterns. Perhaps they would be most active during the warm nights, retreating underground or into insulated shelters during the cold days. Their agriculture, if they developed it, would need to account for the cooling influence of their star. They might grow crops that thrive in the temperature gradients, plants that need both the cold of the star and the warmth of space to complete their life cycles. The cultural implications of cold stars would be profound for any civilizations that arose in their light, or rather, their darkness. Our sun has been worshipped as a god in countless human cultures, seen as the source of life and warmth. But cold stars might be viewed very differently. They might be seen as protectors, shielding planets from the overwhelming heat of space. Or they might be viewed as threats, stealing warmth from the world. The mythology surrounding them would be fascinating to explore. Stories of cold gods and warm demons, of the eternal struggle between the cooling star and the heating void. As we complete this section of our atlas of cold stars, we should remember that each star, whether hot or cold, whether real or imagined, is a unique object with its own history, its own characteristics, its own story. In our universe, we've catalogued millions of stars, and each one is different masses, different ages, different compositions, different fates. The cold stars of our imagined universe would be equally diverse, equally complex, equally worthy of study and wonder. The process of creating this atlas, of imagining these impossible stars, helps us appreciate the real stars of our own universe in a new way. We take for granted that stars are hot, that they pour light and heat into the cold void. But by imagining the opposite, we can see how remarkable this actually is. How strange and wonderful it is that the universe has these massive fusion reactors scattered throughout space, creating the energy that makes planets possible, that makes life possible, that makes us possible. As you drift towards sleep tonight, you might look up at the stars, if you can see them from where you are, and see them with fresh eyes. Each point of light is a massive sphere of plasma, undergoing fusion reactions that would vaporize our entire planet in an instant if we got too close. And yet from here, from this safe distance, they're just gentle lights in the darkness, beautiful and peaceful, and eternal seeming. The cold stars of our imagined universe would be equally magnificent in their own way, dark points against a glowing sky, monuments to an impossible physics that exists only in our imagination, but helps us understand our real universe a little better. The space between stars in our imagined universe is not empty, not void, not the vacuum we know from our own cosmos. Instead, it flows with warmth, like an ocean of temperature without substance, a medium that connects every star, every planet, every mote of dust in a web of gentle heat. These rivers of fire, as we might poetically call them, would define the very nature of space travel, of cosmic structure, of how matter and energy move through this inverted cosmos. Tonight, let us drift along these thermal currents, exploring what it might mean for space itself to be warm, to be filled with a presence rather than an absence, to be something rather than nothing. In our own universe, we've slowly come to understand that space is far from empty, even though it contains so little matter that we call it a vacuum. There are electromagnetic fields permeating every cubic centimetre, gravitational waves rippling through the fabric of space-time, streams of neutrinos passing through everything, dark matter whose nature we still don't understand, and dark energy driving the acceleration of cosmic expansion. But all of this exists in a baseline of cold, that 2.7 Kelvin background that represents the cooled remnant of our universe's hot beginning. In the cosmos we're imagining tonight, that baseline would be warm instead, perhaps hundreds or thousands of degrees above absolute zero, creating an entirely different foundation for cosmic phenomena. Let's imagine what this warm space would feel like if we could somehow experience it directly. Not the violent heat of a flame or the searing temperature of our sun's corona, but something more like floating in a perfectly heated pool where the water matches your body temperature so precisely that you can barely tell where you end and it begins. This cosmic warmth would be gentle, consistent, enveloping. It wouldn't burn or harm. It would simply be a fundamental property of space as basic as its 3 dimensions and the flow of time. Every cubic metre of space would carry this warmth, from the vast voids between galactic superclusters down to the spaces between atoms, if atoms in this universe are structured the way we understand them. The mechanism that maintains this universal warmth presents a fascinating puzzle. In our universe, the cosmic microwave background radiation is a remnant, a fossil growing ever colder as the universe expands. But if space in our imagined cosmos is inherently warm, something must maintain that temperature against the cooling influence of the cold stars. Perhaps the expansion of space itself generates heat in this universe, the stretching of space-time creating thermal energy through some process we can't fathom. Or perhaps there's a field, similar to the Higgs field that gives particles mass in our universe, but this field gives space its temperature, a kind of thermal field that permeates everything and maintains the baseline warmth of the cosmos. Consider how this warm space might flow and move. In our universe, space itself is expanding, carrying galaxies apart like raisins in rising bread dough. In the warm space universe, this expansion might create currents of temperature, rivers of warmth flowing from regions of faster expansion to regions of slower expansion. These thermal currents might be invisible to the eye, but detectable with the right instruments, creating a kind of cosmic weather system on scales we can barely imagine. Galaxies might ride these warm currents like ships on ocean currents, their motion through space influenced not just by gravity, but by the flow of temperature itself. The boundaries between warm space and cold stars would be regions of particular interest and complexity. In our universe, the boundary between a star and space is relatively sharp. The star's surface, the photosphere, marks a clear transition from the dense, hot stellar material to the near vacuum of space. But in our inverted cosmos, the boundary might be more gradual, a zone where the cold of the star and the warmth of space meet and mingle, creating temperature gradients that could extend for millions of kilometers. These boundary regions might shimmer with thermal effects, like the shimmer of heat above a hot road, but in reverse, cold mirages that distort the view of anything beyond them. In these boundary regions, unique phenomena might occur. Perhaps the interaction between hot and cold creates a kind of thermal turbulence, swirls and eddies of temperature that could persist for years or centuries. These might be visible as aurora-like displays, not of light but of temperature variations that sensitive instruments could detect and map. The patterns might be beautiful, mathematical, following the same kinds of fluid dynamics that create the swirls in cream poured into coffee, but on a cosmic scale, and with temperature instead of matter as the flowing medium. Space travel in such a universe would require completely different technologies and approaches than what we've developed. Our spacecraft are designed to retain heat in the cold of space, to protect their occupants and instruments from the near absolute zero of vacuum. But spacecraft in the warm space universe would need to shed heat constantly, to maintain cool temperatures for their occupants and equipment in the face of the eternal warmth surrounding them. They might use the cold stars as cooling stations, approaching them to dump excess heat, before continuing their journeys through the warm void. The propulsion systems for such spacecraft might harness the temperature differential between cold stars and warm space. Just as our heat engines extract work from the flow of heat from hot to cold, their engines might run on the flow from the warm space to cold heat sinks carried on the ship, or they might trail cold collectors behind them like sea anchors, using the temperature difference to generate power. Solar sails in our universe catch the pressure of light from stars. Thermal sails in this universe might catch the flow of heat, using large surfaces that can be oriented to catch or deflect the thermal currents flowing through space. Navigation through warm space would require different kinds of maps and instruments. Instead of star charts showing the positions of bright lights against darkness, navigators would need thermal charts showing the temperature variations across space. They would need to map the thermal currents, the rivers of heat that flow between and around the cold stars, finding the paths that would carry them most efficiently to their destinations. Like ancient Polynesian navigators who could read ocean currents and swells to find islands beyond the horizon, these space navigators would read the subtle variations in the warmth of space to find their way between worlds. Let's imagine following one of these thermal rivers on a journey between star systems. We begin near a cold star, in the relatively cool region created by its presence. As our imaginary ship moves away from the star, the temperature gradually rises, like climbing out of a cool valley into warmer highlands. The transition is smooth at first, but then we encounter the thermal wake of the star, a region where its motion through the warm medium has created disturbances swirls of temperature that our ship must navigate carefully. Beyond the star's immediate influence, we enter what navigators might call the open warm, the vast regions between stars where the temperature is steady and the thermal currents flow in predictable patterns. Here, our ship might deploy its thermal sails, catching a current that will carry us toward our destination. The journey might take years, decades, even centuries, but the consistent warmth of space means that the ship's systems can run indefinitely, extracting energy from the temperature around them, never running out of power as long as they can maintain their cold sinks. As we travel, we pass through regions of different thermal characteristics. Here, a zone where two thermal currents meet, creating a kind of temperature front like weather fronts on Earth, but stable, persisting for millions of years. There, a thermal void, a region mysteriously cooler than the surrounding space, perhaps the remnant of an ancient cold star that died and dissipated millions of years ago. Our instruments detect thermal waves propagating through the medium, perhaps generated by the orbital motion of massive cold stars, spreading outward like ripples on a pond but taking centuries to cross the light years. The interstellar medium in this universe wouldn't be the thin scatter of hydrogen atoms and dust that fills the space between stars in our cosmos. The warmth of space might allow different kinds of matter to exist in the void, perhaps complex molecules that would be frozen solid in our cold universe, but can exist as gases or even plasmas in the warm space. These might form clouds and streams, rivers of matter flowing along with the rivers of heat, creating a rich and complex interstellar environment. These rivers of matter and heat might be where new stars are born, or rather, where new cold stars condense out of the warmth. Perhaps when a thermal current carries enough matter and the temperature drops just slightly, conditions become right for a cold star to begin forming. The process might start with a tiny seed of cold, a quantum fluctuation, or a piece of matter from a dead star around which more coldness accumulates, drawing in matter from the flowing rivers, growing slowly over millions of years until a new cold star is born. The death of cold stars would return their matter to these rivers, enriching them with heavier elements if such elements exist in this universe. When a cold star finally warms and dissipates, its matter wouldn't fall inward as in a supernova, but would spread outward, carried away by the thermal currents, distributed throughout the rivers of fire to eventually become part of new stars, new planets, new possibilities. The cycle of stellar birth and death would be a gentle one, without the violence of our supernova, more like erosion and sedimentation than explosion and collapse. Consider what kinds of structures these thermal rivers might create on the largest scales. In our universe, dark matter forms filaments along which galaxies cluster, creating the cosmic web that defines the large-scale structure of the cosmos. In the warm space universe, thermal currents might create their own kind of web, with galaxies forming along the rivers where temperatures and matter flows are just right for cold stars to form. The voids between these rivers would be regions of static warmth, unchanging for billions of years, while the rivers themselves would be dynamic, evolving, carrying matter and energy across the cosmos. These thermal rivers might connect galaxies in ways that gravity alone cannot. In our universe, galaxies are islands separated by vast voids, interacting only through gravity, and the occasional collision when they pass too close to each other. But if thermal rivers flow between galaxies, they might create connections, pathways along which matter and energy can travel. Civilizations might use these rivers as highways between galaxies, following the thermal currents across millions of light years, journeys that would be impossible in our universe but might be routine in theirs. The study of these rivers would be a major scientific endeavor for any civilization in this universe. They would build instruments to map the thermal currents, to predict their changes, to understand their origins and destinations. They might discover that the rivers follow patterns, that they're not random but organized according to deep principles they're only beginning to understand. Perhaps they would find that the rivers connect in specific ways, creating a kind of thermal circulation system for the entire universe, carrying heat from regions of production to regions of absorption, in a vast cycle that maintains the cosmic balance. Weather in space would be a real phenomenon in this universe, not weather as we know it, with clouds and rain and wind, but thermal weather, with temperature fronts, thermal storms, and seasonal variations as different regions of space warm and cool in complex patterns. A spacecraft travelling through space would need weather forecasts, predictions of thermal conditions along their route. They might need to avoid thermal storms, regions where the usually stable warmth becomes turbulent and dangerous. Or they might seek out such regions, if their technology allows them to harness the energy of thermal chaos. The warm space might also have layers or stratification, like Earth's atmosphere but on a cosmic scale. Perhaps the temperature isn't uniform but varies with distance from the galactic plane, or with distance from the centre of the galaxy. There might be thermal boundaries between regions, like the tropopause in Earth's atmosphere, where the temperature gradient changes abruptly. Crossing these boundaries might require special preparation, different technologies, different ways of thinking about space travel. Let's imagine what it would be like to drift in this warm space, far from any cold star, just floating in the eternal warmth. Without a spacesuit, impossible of course, since the lack of pressure would still be fatal, but imagine if you could somehow experience just the temperature. It would be like the most perfect bath, the most comfortable environment, neither too hot nor too cold, just an endless, enveloping warmth that requires no effort to maintain, no energy to sustain. You could drift for eternity in such a space, carried along by the thermal currents, a mote of consciousness in an ocean of warmth. But this warmth wouldn't be static or boring. As you drift, you would pass through regions of subtle variation, slightly warmer here, slightly cooler there, each change telling a story about what has happened in this region of space. Here, the warmth carries the memory of a cold star that passed through millions of years ago, its cooling influence still detectable as a slight depression in the temperature. There, two thermal currents merge, their different temperatures creating patterns like oil on water, beautiful and ephemeral on cosmic timescales. The philosophy of beings who evolved in such a universe would be profoundly influenced by these rivers of fire. Where we see space as empty and isolating, they would see it as full and connecting. Every point in space would be linked to every other point by the flowing warmth, by the thermal currents that carry energy and perhaps information across the cosmos. They might develop philosophies of cosmic connection, of universal warmth that binds all things together, of rivers that flow from everywhere to everywhere, making the entire universe a single, connected, living system. Their technology would reflect this understanding. Instead of trying to overcome the isolation of space as we do, building faster rockets and more powerful transmitters to bridge the vast distances, they might work with the flowing warmth, designing technologies that use the thermal rivers to carry messages, to transport matter, to connect distant civilizations. They might encode information in temperature variations, sending messages that propagate along the thermal currents, taking centuries to cross the galaxy, but arriving with perfect fidelity, preserved by the stability of the flowing warmth. Now we descend from the vast scales of cosmic rivers to the more intimate scale of planets, moons, and the worlds that might exist beneath skies that glow with warmth rather than sparkle with distant stars. In our inverted universe, where space itself radiates heat and stars are beacons of cold, planets would evolve in environments utterly unlike anything in our cosmos. These worlds would be shaped by the constant tension between the cooling influence of their parent star and the warming embrace of space itself, creating conditions that would challenge our understanding of what makes a world habitable. What allows complexity to arise? What makes life possible? Imagine standing on the surface of such a world as night falls, though we must reconsider what night means in this context. As the cold star sets below the horizon, the sky doesn't darken as ours does. Instead, it begins to glow more prominently with its own inherent warmth, a soft radiance that bathes the landscape in infrared light that eyes evolved in this universe might see as clearly as we see visible light. The horizon shimmers with heat, not the heat rising from the ground as in our deserts, but heat descending from the sky, from space itself, from the fundamental warmth that fills the cosmos. The types of planets that could form in such a universe would depend on their distance from their cold star, but in ways opposite to our own solar system's architecture. Close to the cold star, where its cooling influence is strongest, we might find worlds of perpetual frost, planets where even the warmth of space cannot overcome the deep cold radiating from their parent star. These would be the opposite of our Mercury or Venus, not scorched and lifeless, but frozen in ways that go beyond mere ice, perhaps exhibiting states of matter that can only exist at temperatures approaching absolute zero, while under the pressure of a planetary gravity. On these innermost frozen worlds, the surface might be sculpted by processes we've never seen. Perhaps there would be rivers of liquid helium flowing through valleys of solid nitrogen, or geysers of hydrogen erupting from deep underground, where tidal heating from the cold star's gravity creates just enough energy to liquefy these normally gaseous elements. The atmosphere, if one could exist, might be a thin layer of the only substances that can remain gaseous at such temperatures, creating weather patterns driven not by heat from above but by the minute variations in coldness from their star. Moving outward from the cold star, we would encounter worlds in what we might call the temperate zone, though this term takes on new meaning in our inverted cosmos. These would be planets where the cooling influence of the star and the warming influence of space achieve a kind of balance, creating conditions that might be stable enough for complexity to arise. The day side of these worlds, facing the cold star, would be cooler, while the night side, facing the warm cosmos, would be warmer, the opposite of our own experience where day brings heat and night brings cooling. On such a balanced world, the terminator line between day and night would be a region of particular interest. This wouldn't just be a moving boundary between light and shadow as on Earth, but a dynamic zone where temperature gradients drive powerful atmospheric currents. Winds would blow from the warm night side to the cool day side, carrying heat that would be absorbed by the cold star's influence, then return as cooler air flowing back to be reheated by the cosmic warmth. These circulation patterns would be the primary drivers of weather, creating storms at the terminator that might rage perpetually as the planet rotates. The surfaces of these temperate worlds might be covered with substances that change phase as they move from day to night. Imagine an ocean of some exotic material that's liquid on the warm night side but freezes solid when rotated into the cold starlight. As the planet turns, waves would freeze in place at the terminator, creating a constantly shifting landscape of frozen waves that melt again when they rotate back into night. Erosion would work differently here, with thermal cycling between hot and cold being the primary force shaping the landscape rather than wind and water as on Earth. Life, if it could arise on such worlds, would need to adapt to these dramatic temperature swings. Perhaps organisms would migrate constantly, following the terminator to stay in their preferred temperature zone. Or maybe life would be biphasic, with different metabolisms for day and night, switching between them as the planet rotates. Plants, if we can call them that, might absorb warmth from the cosmic sky during the night, and use the temperature differential during the day to drive their equivalent of photosynthesis. Thermosynthesis, perhaps, extracting energy from heat flow rather than from light. Further from the cold star we would find the hot worlds, planets where the star's cooling influence is weak and the warmth of space dominates. These would be worlds perpetually bathed in heat, where the night sky glows so warmly that the surface never cools, where any volatile substances have long since evaporated into space. These might be desert worlds of crystallized minerals that can withstand the constant heat, or they might be worlds with thick atmospheres that have reached equilibrium with the cosmic warmth, creating greenhouse conditions that would make Venus seem frigid by comparison. On these outer hot worlds, if they have atmospheres, the air itself might glow with heat, creating a permanent aurora not of magnetic particles, but of thermal radiation. The surface might be covered with formations created by thermal expansion and contraction, as the weak influence of the cold star creates tiny temperature variations. Mountains might grow through thermal processes we don't understand, rocks swelling with heat and creating uplift, or perhaps the opposite, with cooling creating contraction that builds mountain ranges through compression. Let's consider the moons of planets in this universe, particularly those orbiting gas giants far from their cold star. In our solar system, moons like Europa and Enceladus are covered in ice, but harbour liquid oceans beneath, heated by tidal friction from their parent planet's gravity. In the warm space universe, such moons might have the opposite structure, liquid surfaces maintained by the cosmic warmth, but solid cores cooled by some process we can't quite imagine. Or perhaps the interplay between the cold star, the warm space, and the gravitational heating from their parent planet would create incredibly complex thermal environments with multiple layers of different phases of matter. The gas giants themselves would be fascinating in this universe. In our cosmos, Jupiter and Saturn are warm inside from the heat of their formation, slowly cooling over billions of years. but gas giants in a warm space universe might be cold inside, perhaps with solid cores of frozen hydrogen, surrounded by layers that get progressively warmer toward the surface where they meet the warm space. The Great Red Spot on our Jupiter is a storm driven by heat from below. Their equivalent might be a Great Blue Spot, a region of unusual coldness creating a different kind of atmospheric vortex. Ring systems around, planets would behave differently too. Saturn's rings are made of water ice, kept frozen by the cold of space. Rings in the warm space universe might be made of materials that can remain solid despite the heat, perhaps metals or ceramics, or they might be composed of droplets of liquid held in orbit, creating shimmering veils around planets rather than solid rings. The dynamics of such rings would be beautiful to model, with particles constantly evaporating and condensing, exchanging material with the warm space around them. The formation of planets in this universe presents interesting questions. In our cosmos, planets form from disks of gas and dust around young stars, with temperature gradients determining what kinds of planets form where. Rocky planets close in where it's too hot for ices, gas and ice giants farther out, where volatile materials can condense. The process in a warm space universe might be reversed or completely different. Perhaps planets form first as accumulations of cold matter that then attract the attention of cold stars, which capture them gravitationally. Or maybe planets condense out of the warm medium of space when local conditions allow temporary cooling, like dew forming on a warm night. The geological processes on these worlds would be driven by different forces than on Earth. Our plate tectonics is driven by heat from radioactive decay in the interior and residual heat from Earth's formation. But on a world in warm space, the interior might be cooled by the planet's formation process, while the exterior is heated by space. This might create an inverted thermal gradient, with heat flowing inward rather than outward. Volcanoes might erupt cold materials from the interior, creating flows of liquid nitrogen or methane that freeze solid when they reach the warm surface. Atmospheres on these planets would face unique challenges. In our solar system, atmospheres are lost to space when molecules achieve escape velocity, usually because they're heated by the sun. In the warm space universe, atmospheres might be constantly heated by the cosmic warmth, making it difficult for planets to retain gaseous envelopes unless they have very strong gravity or very heavy atmospheric molecules. Alternatively, the cold stars might help planets retain their atmospheres by cooling the upper layers, creating a kind of cold trap that prevents gases from escaping. The chemistry possible on these worlds would be exotic compared to Earth. Different temperature ranges allow different chemical reactions, different stable molecules, different forms of complexity. Water, so crucial to life on Earth, might not be liquid at any point on some of these worlds, while other substances we think of as gases or solids might serve the role of a liquid medium for chemical reactions. Silicon chemistry, impossible at Earth temperatures, might dominate on the hot worlds. Exotic ice chemistry might rule on the cold worlds, and in the temperate zones, who knows what complex chemistry might arise from the cycling between hot and cold? Weather patterns on these worlds would be driven primarily by the interaction between cosmic warmth and stellar cold, rather than by stellar heating as on Earth. Hurricanes might form not over warm oceans, but at the boundaries between regions of different temperature. Rain might fall upward on some worlds, with condensation occurring at the surface and droplets being carried aloft by the warm air rising to meet the cosmic heat. Seasons, if they exist, would be complex functions of orbital distance, axial tilt, and perhaps other factors we haven't considered. The night sky from these worlds would be a wonder to behold. Instead of stars as points of light against darkness, observers would see cold stars as dark spots against a glowing background, like looking at the negative of our night sky. The planets in the system might be visible as cooler or warmer spots depending on their distance from the cold star and their own thermal properties. Comets might leave trails of warmth rather than tails of ice and dust. Meteor showers might be visible as streaks of temperature change rather than streaks of light. Any civilizations that arose on these worlds would have a completely different relationship with their environment than we do. They couldn't use fire the way we do. What would burn in a universe where space itself is hot? Their technology would need to be based on different principles, perhaps using thermal gradients the way we use electrical potential differences. Their agriculture would need to manage heat rather than harness it. Their architecture would focus on insulation and cooling rather than heating. the way such civilizations might detect other worlds would be different too. We look for exoplanets by watching for the dimming of stars as planets pass in front of them, or by detecting the wobble of stars caused by orbiting planets' gravity. They might look for the warming of cold stars as planets block some of the cosmic heat from reaching them, or they might detect planets directly by their thermal signatures against the warm background of space. Space exploration from these worlds would face different challenges than we face. Launching from a world that's being heated from above rather than cooled might require different rocket designs, different fuels, different trajectories. Once in space, spacecraft wouldn't need heating systems but rather cooling systems. Solar panels wouldn't work, but thermal panels that extract energy from the temperature differential between the warm space and cold collectors might provide power. The search for life in such a universe would focus on different biosignatures than our search. We look for oxygen in atmospheres, for the green of chlorophyll, for radio signals from technological civilizations. They might look for unusual patterns of heat absorption or emission, for chemicals that could only be maintained far from thermal equilibrium by living processes, for structures that manage heat in ways that suggest intention rather than natural processes. In this universe of cold stars and warm space, the entire endeavour of astronomy, of understanding the cosmos beyond one's own world, would require fundamentally different approaches than those we've developed over centuries of studying our hot star universe. The instruments built by curious minds in this inverted cosmos wouldn't seek to gather light from distant sources, but rather to map the subtle variations in the all-pervading warmth, to detect the shadows of cold cast by distant stars, to read the thermal story written across the sky. Let us explore these instruments, these tools of cosmic discovery, and through them understand how beings in such a universe might come to comprehend their place in the cosmic order. The most basic instrument of astronomy in our universe is the eye, evolved to detect the light from our hot sun and the reflected light from objects around us. But in a universe where space glows with warmth and stars are cold, eyes might have evolved differently. Perhaps they would see in the infrared spectrum, detecting heat rather than visible light. The pupils of such eyes wouldn't dilate in darkness but in coldness, opening wide to gather more thermal radiation when in the shadow of a cold star, contracting when exposed to the full warmth of open space. The very concept of colour would be different. Instead of the spectrum from red to violet that we know, they might perceive a spectrum of temperatures, with different wavelengths of infrared radiation creating a rich palette of thermal colours we can't imagine. The first telescopes in this universe wouldn't be tubes with lenses or mirrors designed to focus light, but perhaps chambers designed to detect and amplify temperature differences. Imagine a large, insulated cavity with incredibly sensitive thermal sensors at its focus, capable of detecting variations of millionths of a degree from the baseline warmth of space. Such an instrument pointed at the sky wouldn't see points of light, but rather subtle variations in the cosmic warmth. Cooler regions where cold stars block or absorb the background heat. Warmer regions where thermal currents concentrate energy. The development of such thermal telescopes would follow a different path than our optical telescopes, where we progressed from small refractors to large reflectors, from ground-based to space-based instruments. They might progress from simple thermal detectors to complex arrays of sensors that can map temperature variations across the sky in exquisite detail. The equivalent of our adaptive optics, which corrects for atmospheric turbulence, might be adaptive thermal systems that correct for the heat shimmer of their planet's atmosphere, allowing them to detect the subtle thermal signatures of distant cosmic objects. Space-based observatories in this universe would face opposite challenges from our space telescopes. The Hubble Space Telescope needs to be kept at stable temperatures, protected from the extreme cold of space and the heat of the sun. But a space telescope in the warm space universe would need to be cooled, perhaps to temperatures even lower than the cold stars themselves, to achieve the sensitivity needed to detect minute thermal variations. Such observatories might orbit far from any cold star, in the warmest regions of space where the background is most uniform, making it easier to detect anomalies. These orbital observatories might be vast structures, kilometers across, with cooling systems that would seem magical to us. Perhaps they would use the principle of the cold stars themselves, whatever mechanism allows those stars to maintain their low temperatures in the warm cosmos. The telescopes might be surrounded by shells of supercooled material, creating zones of extreme cold that make their sensors incredibly sensitive to any thermal input. They might need to be isolated from their own support systems, with the instruments floating free in the centre of the structure, connected only by materials that conduct neither heat nor cold. The data from these instruments would create images unlike anything our telescopes produce. Instead of the gorgeous full-colour images of nebulae and galaxies that we're familiar with, their images might show thermal maps, with false colours representing different temperatures. A galaxy might appear as a swirl of cool blues and purples against a warm red background, with individual cold stars visible as dark spots within the galactic disk. Nebulae, if they exist in this universe, might appear as regions of thermal turbulence, where hot and cold mix in complex patterns that reveal the dynamics of star formation or stellar death. Radio astronomy in this universe might not exist as we know it, or it might be transformed into something else entirely. Radio waves, being electromagnetic radiation like light, might behave differently in a universe with different fundamental properties. Perhaps instead of radio telescopes, they would have thermal wave detectors, instruments that can detect the propagation of temperature changes through this medium of warm space. These waves might travel faster or slower than light, creating a different kind of astronomy that can see events before or after they're thermally visible. The search for exoplanets would require different techniques. Our transit method, watching for the dimming of stars as planets pass in front of them, would become a warming method, watching for the slight increase in a cold star's temperature as a planet blocks some of the cosmic warmth from reaching it. The radial velocity method might still work, detecting the wobble of cold stars caused by orbiting planets, but the Doppler shift might affect thermal radiation rather than light. Direct imaging of exoplanets might be easier in some ways, as planets might stand out more, clearly against the uniform warm background of space than they do against the glare of their parent stars in our universe. Spectroscopy, the technique that allows us to determine the composition of distant objects by analysing their light, would need to be reimagined. Instead of looking at absorption and emission lines in optical spectra, astronomers might analyse thermal spectra, the specific ways different materials absorb and emit heat. Each element, each molecule, might have a unique thermal signature, a specific pattern of infrared wavelengths it preferentially absorbs or emits. Building libraries of these thermal spectra would be a massive undertaking, requiring laboratory work at extreme temperatures to understand how materials behave in the conditions of their universe. The instruments used to study the cosmic thermal background, their equivalent of our cosmic microwave background, would be marvels of sensitivity. They would need to detect variations of perhaps 1 part in a million from the baseline temperature of space, mapping these tiny fluctuations across the entire sky. These maps would reveal the large-scale structure of their universe, the thermal echoes of whatever process created their cosmos, the seeds from which galaxies and larger structures grew. The discovery of this thermal background would be as revolutionary for them as the discovery of the CMB was for us, confirming their theories about the origin and evolution of their universe. Gravitational wave detectors might exist in this universe, but they would face different challenges. Our LIGO and Virgo detectors must be isolated from seismic vibrations, thermal noise, and other sources of interference. Their gravitational wave detectors would need to be isolated from thermal fluctuations, from the constant warmth of space that might mask the tiny distortions of space-time caused by merging cold stars or other massive objects. Perhaps they would be built at the poles of frozen planets, where the cold star's influence is strongest and the cosmic warmth is most effectively blocked. The particle physics experiments in this universe would be fascinating to contemplate. Our particle accelerators smash particles together at high energies, recreating the conditions of the early universe when it was hot and dense. Their particle accelerators might do the opposite, cooling particles to extreme temperatures to study the fundamental forces under conditions of extreme cold. They might discover that particles behave differently at different temperatures, that the fundamental forces themselves are temperature dependent in ways our physics doesn't predict. Neutrino detectors in our universe are built deep underground, using vast tanks of water or ice to detect the rare interactions of these ghostly particles. In the warm space universe, neutrino detectors might need to be built in the shadows of cold stars, using the star's cooling influence to create conditions where neutrinos interact more readily with matter. Or perhaps neutrinos in that universe carry thermal information, and detecting them reveals the temperature history of distant cosmic events. The computers and data processing systems needed to analyze the information from all these instruments would themselves be challenged by the warm universe. Our computers generate heat and need cooling systems, but in a universe where space itself is warm, getting rid of excess heat would be a constant challenge. Perhaps their computers would operate on different principles, using the flow of heat itself as a computational medium, with thermal gradients representing bits of information and heat flow representing computation. The way data is stored and transmitted would be different too. We encode information in electromagnetic signals, radio waves, light pulses in fiber optics, electrical signals in wires. They might encode information in temperature variations, sending messages as waves of heat and cold through specially designed conductors. Long-distance communication might use the thermal currents in space itself, encoding messages in temperature patterns that propagate along these cosmic rivers, taking years or centuries to cross interstellar distances but arriving intact. The observatories themselves, the buildings and facilities that house these instruments, would be architectural marvels designed to manage the constant influx of heat from space. On a planet's surface, an observatory would need to be insulated from both the cosmic warmth and any local heat sources. The buildings might be covered in materials that reflect infrared radiation, or they might use active cooling systems that pump heat into deep underground reservoirs. The domes that protect telescopes in our world might be cooling domes in theirs, maintaining a pocket of cold air above the instrument to minimize thermal interference from the atmosphere. Space missions in this universe would carry instruments we can barely imagine. Where our space probes carry cameras and spectrometers, theirs might carry thermal mappers and temperature wave detectors. A mission to a cold star would need to be heavily insulated, protected from the extreme cold, while a mission to the warm voids between stars might need cooling systems that can function far from any cold source. Landing on planets would require heat shields not to protect from the friction of atmospheric entry, but to protect from the constant warmth of space during the journey. The way these civilizations share and collaborate on astronomical observations would create different kinds of scientific communities. Our astronomers share images and spectra, coordinate observations of transient events, build databases of stellar properties. Their astronomers might share thermal maps, coordinate observations of temperature waves propagating through space, build databases of thermal signatures. The global, or interplanetary, or interstellar, collaboration required to study their universe would face the same challenges of distance and time that we face, but with the added complexity of managing data that represents temperature rather than light. Amateur astronomy in this universe would be a different hobby entirely. Instead of small optical telescopes in backyards, amateur astronomers might have thermal detectors, perhaps cooled by thermoelectric systems, or even just by exposure to the shadow of their cold star during the day. They might track the thermal cycles of nearby cold stars, discover new patterns in the cosmic warmth, contribute observations to professional researchers studying the thermal universe. The beauty they would seek wouldn't be the pinpoint lights of stars or the fuzzy patches of nebulae, but the subtle gradients of temperature painted across their sky, the dance of hot and cold that defines their cosmos. The philosophical implications of these observations would shape their understanding of their place in the universe. Where we've discovered that we orbit an ordinary star in an ordinary galaxy in an ordinary part of the universe, they might discover that they exist in an ordinary temperature gradient in an ordinary thermal current in an ordinary region of the cosmic warmth. The Copernican principle would apply just as strongly. They are not the centre of the universe, not special, not unique, but the details would be entirely different. The search for extraterrestrial intelligence would use different methods than our SETI programs. Instead of looking for radio signals or laser pulses, they might look for artificial patterns in thermal emissions, for temperature modulations that couldn't be natural. They might broadcast their own presence not with radio waves, but with controlled thermal pulses, creating patterns of hot and cold that propagate through space, announcing to any listening civilization that intelligence has arisen on their world. The instruments we've imagined here, thermal telescopes, temperature wave detectors, cosmic heat mappers, are all speculative, based on extending our understanding of physics into a realm where the basic rules are different. But the drive to build such instruments, to understand the universe beyond one's own world, would be the same as the drive that led humans to build the first telescopes, to launch the first space probes, to ask the fundamental questions about our place in the cosmos. The tools would be different, but the curiosity would be the same, The wonder would be the same. The gradual expansion of knowledge from one small world to an understanding of the vast cosmos would follow the same patient, persistent path that science follows in any universe. As we contemplate these instruments and the observations they would make, we're reminded that science is not just about the specific facts we discover, but about the process of discovery itself. Whether studying a universe of hot stars and cold space, or cold stars and hot space, the scientific method remains the same. Observe, hypothesize, test, refine. The instruments are just tools that extend our senses, whether those senses detect light or heat, or something else entirely. The real instrument of discovery is the curious mind that asks, what's out there, and then builds the tools to find out. The history of astronomy in this thermal universe would be a story of gradually improving sensitivity, of detecting ever subtler variations in temperature, of seeing ever farther into the cosmic distance and the cosmic past. Each new generation of instruments would reveal new phenomena, new mysteries, new questions that would drive the development of even better instruments. The cycle of discovery would continue, whether driven by light or by heat, by the eternal human or non-human desire to understand the cosmos we inhabit, and perhaps, in some deep way, the discoveries would converge on similar truths. The universe, whether hot or cold, whether light or dark, is vast and ancient and beautiful. Life, however it arises, is rare and precious. Intelligence, capable of building instruments to study the cosmos, is rarer still. The journey from ignorance to knowledge, from mystery to understanding, is the same journey whether travelled by beings who see light or beings who sense heat. The cosmos reveals itself to any who have the patience and ingenuity to look, to measure, to wonder, to understand. Now we drift into deeper waters, into questions not just of physics and astronomy, but of philosophy and meaning, of what it might feel like in your very bones to exist in a universe where cold stars hang in warm space, where the fundamental rhythms of existence are reversed from everything we know. Time itself might flow differently here, not in its direction. We're not imagining a universe where time runs backward, but in how it's perceived, how it's measured, how it shapes the consciousness of beings who evolved under cold suns and warm skies. Tonight, let us explore these deeper currents, these questions of experience and meaning that would define life in such a cosmos. Consider first how the experience of time might differ for beings who grew up with cold stars and warm space. We mark our days by the sun's movement across the sky, our months by the moon's phases, our years by Earth's orbit around the sun. These celestial rhythms are encoded in our biology, our circadian rhythms, our monthly cycles, our seasonal patterns of behaviour. We are creatures of a hot star universe, shaped by millions of years of evolution under the alternating warmth and coolness of day and night. But in a universe where the star cools rather than warms, where night brings heat rather than cold, the very feeling of time's passage would be different. Imagine waking on a world in this universe as the cold star rises. You wouldn't wake to warmth and light flooding through your window, but to a gradual cooling, a drawing away of heat that might feel like the universe itself is inhaling, pulling warmth up into the sky. The morning wouldn't energize but might tranquilize, encouraging a slow, contemplative start to the day. Perhaps biological rhythms would be reversed, with beings most active during the warm nights and dormant during the cold days, or perhaps they would have evolved entirely different patterns, active at the terminator where cold and warm meet, following that zone of temperature gradient around their planet as it rotates. The measurement of time in such a universe might not rely on the visible movement of celestial bodies but on thermal cycles. Instead of sundials that track shadows, they might have thermal dials that track temperature gradients. Instead of mechanical clocks based on pendulums or springs, they might develop thermal clocks based on the predictable flow of heat from warm to cold regions. The very concept of noon, the moment when the sun is highest in the sky, might be replaced by something like peak cold, the moment when the cold star's influence is strongest. Midnight wouldn't be the darkest time but the warmest, when the full heat of space pours down unimpeded by the cold star's presence. Memory itself might be structured differently in minds that evolved in such a universe. We often associate memories with temperatures, a warm summer day, a cold winter morning, the heat of embarrassment, the chill of fear. But if the fundamental associations were reversed, If warmth came from the void and cold from stars, the emotional resonance of memories might be entirely different. Childhood memories might be of warm nights spent under the glowing sky, of cold days huddled near thermal vents, of the first time you saw a cold star rise and felt its chill touch your skin. The metaphors we use for memory, burning memories, frozen moments, would all be reversed or transformed into something we can barely imagine. The way such beings would understand their own consciousness might differ profoundly from our self-understanding. We often think of consciousness as a light in the darkness, awareness illuminating the void of non-being, but in a universe where the void itself is warm and glowing, consciousness might be understood as a point of coolness in the warmth, a place where the universal heat is organized into thought and intention. They might see thinking not as generating heat, as our brains do, but as creating order in heat, cooling it into patterns that represent ideas and feelings. The development of culture and meaning in such a universe would follow different paths than in ours. Our ancestors gathered around fires for warmth and safety, and fire became central to human culture. The hearth, as the center of the home, the eternal flames of temples, the Olympic torch, the metaphorical fires of passion and creativity. But in a universe where space itself provides warmth, fire might never have been discovered or might have a completely different cultural significance. Perhaps they would gather in cool spaces for comfort, and cold would become the center of cultural life. Pools of cooled air or liquid, shadows cast by structures that block the cosmic warmth, underground chambers where the cold star's influence can be felt even during the warm night. The religions and philosophies that might arise in such a universe present fascinating possibilities for contemplation. Where many of our religions associate light with good and darkness with evil, warmth with life and cold with death, their associations might be completely different. Perhaps they would worship cold deities who provide relief from the eternal warmth, or perhaps they would see the warm cosmos as a nurturing parent and the cold stars as necessary but harsh teachers. Their creation myths might speak of a universe that began in perfect uniform warmth and gradually differentiated into hot and cold rather than our Big Bang that started hot and is cooling down. Think about how they might conceptualize death and afterlife. We often speak of the cold hand of death or the warmth of life, but in their universe, death might be associated with a return to the universal warmth, a dissolution back into the cosmic heat from which all things emerged. The afterlife might be imagined not as a bright place of light, but as a realm of perfect temperature, neither too hot nor too cold, where consciousness exists in thermal equilibrium. Or perhaps they would imagine multiple afterlives sorted by temperature, with different fates awaiting souls depending on how they managed the balance of hot and cold during their lives. The development of mathematics and science would follow different paths, though perhaps arriving at similar destinations. Where Galileo watched pendulums and rolling balls, their Galileo might have watched thermal gradients and heat flows. Where Newton was inspired by a falling apple, their Newton might have been inspired by the way heat rises from a surface into the warm sky. The laws of thermodynamics would be discovered early and be central to their physics, while mechanics might come later. They might understand entropy and information theory before they understand momentum and force. The concept of progress itself might be different. We often associate progress with generating more energy, with harnessing fire, then steam, then electricity, then nuclear power. But in a universe where energy in the form of heat is abundant, progress might be associated with managing and organizing that energy, with creating spaces of controlled temperature where complex processes can occur. Their industrial revolution might not be about burning coal to generate steam, but about creating massive cooling systems that allow for precision manufacturing in controlled cold environments. Art and aesthetics in such a universe would celebrate different qualities than ours, where we find beauty in the play of light and shadow in bright colours and dark contrasts. They might find beauty in thermal gradients, in the subtle shift from warm to cool, in patterns that are invisible to eyes that see light, but obvious to senses that detect heat. Their paintings might be created with materials of different thermal properties, creating images that change as the ambient temperature changes. Their sculptures might be designed to channel heat in particular ways, creating thermal signatures that are as important as their physical shapes. Music might exist, as sound waves would still propagate through atmospheric gases, but the instruments might be different. Instead of strings that vibrate or drums that resonate, They might have thermal instruments that create sound through the expansion and contraction of materials or through the movement of air caused by temperature differentials. The concert halls might be designed not just for acoustics, but for thermal properties, with the temperature of the space affecting the quality of the sound in ways that are part of the artistic experience. The literature of such a universe would employ different metaphors, different symbolic systems. Where we write of burning passion or cold indifference, they might write of the passion of the void or stellar indifference. Their poetry might celebrate the warm night rather than the bright day, might find meaning in thermal currents rather than in the movement of celestial lights. Their epic tales might be of heroes who ventured into the cold hearts of stars or who rode the thermal rivers between worlds. The concept of home would carry different meanings. For us, home is often associated with warmth, the hearth, the family warmth, coming in from the cold. For them, home might be about achieving the perfect temperature balance, about creating spaces that are neither too influenced by the cold star nor too exposed to the warm void. Architecture would be primarily about thermal management, with buildings designed to channel, block, or moderate heat flows. The wealthy might live in perfectly climate-controlled environments, while the poor might be subject to the full range of thermal variation. Consider how they might think about the passage of ages, the deep time of cosmic history. We divide our universe's history into epochs based on temperature. The Planck epoch, when the universe was unimaginably hot. The cosmic dark ages, when it cooled enough for atoms to form. The stelliferous era, when stars shine. The degenerate era, far in the future, when all stars have died. Their cosmic history might be divided differently, perhaps an initial cold epoch gradually warming, or a cycle of warming and cooling that has no beginning or end. They might not fear the heat death of the universe as we do, but perhaps the cold death, when all temperature gradients have equalized and no more energy can flow. The way they would understand causation and free will might be influenced by living in a universe where heat is abundant and cold is rare. We often think of ourselves as struggling against entropy, creating temporary islands of order in a universe trending toward disorder. They might see themselves as part of the natural flow of heat, with consciousness arising not in opposition to entropy, but as a natural consequence of thermal flows. Free will might not be about choosing to act against nature, but about choosing how to channel the inevitable flow of heat through one's life and actions. Their understanding of information and computation might be thermodynamic from the start. While we discovered the connection between information and entropy relatively recently, they might understand from the beginning that information is about the organization of heat, that computation is about directing thermal flows, that consciousness itself is a pattern of temperature differentials. Their computers, as we mentioned earlier, might be thermal devices, but more than that, their whole concept of what computation means might be grounded in thermodynamics rather than in logic and mathematics. The social structures that would emerge in such a universe might be organized around thermal resources rather than material ones. Instead of controlling land or water or oil, power might come from controlling cold sources or managing heat flows. Wars might be fought over access to cold stars or over the right to block another nation's access to cosmic warmth. Economic systems might be based on thermal credits, with wealth measured not in gold or currency, but in the ability to maintain comfortable temperatures. The exploration of space would carry different meanings for them. Where we see space exploration as venturing out into the cold darkness, they would see it as venturing into the warm brightness. The courage required wouldn't be to face the cold, but to face the heat, to leave the tempering influence of their cold star and venture into regions where only the cosmic warmth exists. The reasons for space exploration might be different too, not seeking new resources or escaping a dying world, but perhaps seeking new temperature regimes, new kinds of cold stars, new ways of experiencing the thermal universe. Let us now release ourselves from the bonds of analysis and explanation, from the need to understand and categorize, and simply drift through this warm cosmos we've imagined, floating like a mote of consciousness in an endless sea of gentle heat. This is the most peaceful part of our journey, where we stop trying to make sense of this impossible universe and simply experience it, letting our minds wander through the warm darkness that isn't dark, past the cold stars that don't shine, through regions of space that embrace rather than isolate. Close your eyes if you wish, or let them rest softly unfocused, and drift with me through the ember sea of this inverted cosmos. We begin our drift far from any cold star, in the deep warmth between galaxies, where space has been undisturbed for billions of years. Here the temperature is perfectly uniform, unchanging, eternal. There are no landmarks, no variations, just an endless sameness that might seem monotonous, but is instead profoundly peaceful. We float here, weightless not just in body but in mind, freed from the need to navigate or orient ourselves. In the quiet depths of space, in this impossible warmth, we find a kind of cosmic meditation, a state where thought slows and spreads out like heat, diffusing through a medium. The warmth here isn't aggressive or overwhelming. It's precisely the right temperature, though what that temperature might be, we cannot say. It's the temperature of comfort, of ease, of existence without struggle. As we drift, we become aware that this warmth has always been here, will always be here, patient and eternal. It was warm before the cold stars formed, and it will be warm after they've all dissipated back into the cosmic medium. This is the baseline of existence in this universe, the fundamental state from which all variation emerges and to which all variation returns. Slowly, so slowly that at first we don't notice, we begin to detect a subtle current in the warmth. Not a movement of matter, for we're still in the near vacuum between galaxies, but a movement of temperature itself, a gentle flow of heat from somewhere to somewhere else. We let ourselves be carried along by this thermal current, not swimming or steering, just drifting, allowing the universe to take us where it will. The current is patient, unhurried, moving at speeds that make glaciers seem hasty. We could drift like this for millions of years and barely cross the void between galaxy clusters. As we drift, we become aware of others drifting with us, not beings or objects, but patterns in the warmth, like us but not us, temporary organizations of temperature that might or might not be conscious. Are these the thoughts of the universe itself, thermal patterns that arise spontaneously in the flowing heat? Are they other dreamers like us drifting through this imagined cosmos? Or are they something else entirely, something that can only exist in a universe where space is warm and stars are cold? We drift together, separate but connected, each following our own path through the warmth but influenced by each other's presence. Somewhere in the cosmic darkness, though darkness is the wrong word in this glowing universe, we sense the approach of structure. The perfect uniformity of the deep void begins to show variation, subtle at first, then more pronounced. We're approaching a galaxy, a vast spiral of cold stars suspended in the warmth. From a distance, it appears as a region of slightly cooler temperature, a shadow in the glow, but as we drift closer, we begin to resolve its structure. The spiral arms are rivers of relative cold, channels where cold stars cluster more densely, while between them, the warmth flows in eddies and currents we can feel but not see. We enter the galaxy's outer reaches, where cold stars are sparse and the warmth still dominates. Here, ancient stars near the end of their existence drift in slow orbits, their coldness less pronounced than younger stars, as if they're gradually warming toward equilibrium with space. Some have already crossed that threshold, no longer cold enough to be called stars, just slightly cool regions that remember what they once were. We drift past one of these dying stars, feeling the subtle temperature gradient that still surrounds it, the last vestige of its stellar identity. Deeper into the galaxy now, we encounter our first truly cold star, and the sensation is extraordinary. The warmth we've been drifting through suddenly has a counterpoint, a presence that defines itself by absence, by the heat it absorbs rather than emits. We don't approach too closely. The cold would be uncomfortable, perhaps dangerous to our drifting consciousness, but we orbit it at a safe distance, feeling how it shapes the warmth around it, how it creates currents and gradients in what would otherwise be uniform heat. Around this cold star, we discover planets, worlds we can sense by their thermal signatures. One is almost as cold as its star, a frozen world where the star's influence dominates completely. Another is warmer, finding a balance between stellar cold and cosmic heat. A third is hot, barely influenced by its distant star, cooking in the cosmic warmth. Each world is unique, each has its own thermal story, its own pattern of heat and cold that speaks of its history, its composition, its possible futures. We leave the planetary system and continue our drift through the galaxy. passing through regions of different stellar density. In the sparse regions, the warmth flows freely, creating what we might call thermal meadows, open spaces where heat can spread and equilibrate. In the dense regions, the cold stars create complex patterns, thermal labyrinths where the temperature changes dramatically over short distances. We navigate these regions by instinct, always finding the paths of comfortable temperature, neither too hot nor too cold. In the quiet depths of space, somewhere in the cosmic darkness that glows with its own warmth, we encounter a stellar nursery, a region where new cold stars are being born. But the process is so slow, so gradual, that we could watch for millennia and barely see any change. Still, we can sense it happening. The slow condensation of cold from the warmth, the gradual organization of matter and temperature into the patterns that will become stars. It's like watching clouds form in reverse, or ice crystals growing in slow motion, but on a scale so vast that our minds can barely comprehend it. We drift onward, leaving the stellar nursery behind, and find ourselves approaching the galaxy's center. Here, the density of cold stars increases dramatically, and the temperature drops noticeably. It's still warm, by absolute standards, but cool compared to the intergalactic void we started in. The cold stars are so numerous here that their individual influences overlap, creating a kind of generalized coolness, a refrigerated zone at the galaxy's heart. And at the very center, we sense something else, something that's neither hot nor cold, but somehow outside the normal rules of temperature. Perhaps a massive black hole, or something even stranger that can exist in this impossible universe. We don't approach the galactic center too closely. There's something about it that suggests boundaries should not be crossed, limits that should not be tested. Instead, we let ourselves be caught by one of the spiral arms, a current of organized motion that carries us back out toward the galaxy's edge. The journey outward is different from the journey inward, following different thermal paths, showing us different vistas of cold stars and warm voids. We pass double star systems where two cold stars orbit each other, creating complex patterns of temperature between them. We pass through regions where stars have died, and their matter is dispersing back into space, creating temporary clouds of intermediate temperature. Eventually we emerge from the galaxy, back into the intergalactic medium, but we're not in the same place we started. We've been changed by our passage through the galaxy, carrying with us some subtle influence of all those cold stars, all those thermal gradients. The uniform warmth of intergalactic space feels different now, not empty but full of potential, ready to give birth to new structures, new patterns, new possibilities. We continue our drift, but now we're more aware of the subtle variations in the warmth. Here, a slightly cooler region that might be the thermal wake of a galaxy that passed through millions of years ago. There, a slightly warmer zone where thermal currents converge. We begin to understand that even the seemingly uniform warmth of space has structure, has history, has stories to tell if we're patient enough to listen. Time passes. How much time we cannot say. In this state of drift, seconds and centuries feel the same. We might have been drifting for moments or for eons. The universe around us continues its slow evolution. Cold stars forming and dying, galaxies rotating through their cycles, the large-scale structure of the cosmos slowly evolving. But we're not concerned with these changes. We're simply present, simply drifting, simply being in this warm cosmos that we've imagined into existence. Somewhere in our drift we encounter something unexpected, a region where the temperature oscillates, pulsing with a slow rhythm like a cosmic heartbeat. The period is long, perhaps thousands of years per cycle, but we can feel it, warming and cooling, as regular as clockwork but as natural as breathing. What causes this? Is it some kind of thermal star that pulses in temperature? Is it the interaction of multiple influences creating a standing wave of heat? We don't know, and in our drifting state, we don't need to know. We simply experience it, let it wash over us, become part of its rhythm for a while before drifting on. We pass through regions where the warmth seems to carry information, patterns that are too regular to be random but too complex for us to decode. Are these messages from some cosmic intelligence? Are they the thermal equivalent of gravitational waves carrying news of distant cosmic events? Or are they just patterns we're imposing on randomness, our pattern-seeking minds finding meaning where none exists? In our drifting state, all possibilities seem equally valid, equally beautiful. At some point in our journey, and journey is perhaps too strong a word for this aimless, peaceful drifting, we become aware that we're not alone, not in the sense of encountering other beings, but in the sense that the entire warm cosmos is somehow aware, somehow present, somehow participating in our drift. The warmth isn't just a passive medium we're moving through, but an active participant in our experience. It responds to our presence, subtle changes in temperature marking our passage, the universe acknowledging our existence in its own quiet way. We drift past structures we can't quite understand, organizations of matter and temperature that don't fit any category we know. Are they natural phenomena we haven't imagined yet? Are they artifacts of some cosmic civilization that has learned to build with temperature itself? Are they illusions, mirages created by the complex interplay of heat and cold? We don't investigate, don't analyze, just observe and drift on, adding these mysteries to our collection of unexplained wonders. The rhythm of our drift becomes hypnotic, meditative. Warm regions flowing into cool regions warming back to equilibrium, the eternal dance of temperature that defines this universe. We're no longer observers of this dance, but participants in it, our own imagined presence affecting the temperature around us, creating our own small contribution to the cosmic thermal patterns. We're part of the embassy now, dissolved into it, our consciousness spread out through the warmth, like heat diffusing through a medium. In this state, the distinction between self and universe begins to blur. Are we drifting through the warm cosmos, or is the warm cosmos drifting through us? Are we imagining this universe, or is it imagining us? The questions have no answers, or perhaps the questions and answers are the same thing, just temperature patterns in an infinite sea of warmth, temporary organizations that arise and dissipate like thermal fluctuations in the cosmic medium. And now, gently, slowly, like a tide retreating from a shore, we begin our return journey, not through space, for in our imagination we never really left, but through layers of possibility, back from the universe where stars are cold and space is warm, back to our own familiar cosmos where stars blaze with nuclear fire and space spreads out in cold darkness. The transition is gradual, peaceful, like waking slowly from a deep dream, carrying with us not the specific details, but the feeling of having been somewhere else, of having experienced something profound and strange and beautiful. As we return to our own universe, we bring with us a new appreciation for the arbitrary nature of what we call reality. The laws of physics that govern our cosmos, the constants that determine how matter and energy behave, the fundamental forces that shape everything from subatomic particles to galaxy clusters, all of these could, conceivably, have been different. The universe could have been arranged in countless other ways, and in some of those arrangements perhaps, consciousness and wonder could still arise, beings could still look up at their skies, whatever those skies might look like, and ask the eternal questions about existence and meaning. The stars above us now, if you can see them from where you are, shine with their familiar light. But perhaps they seem different somehow, more remarkable for being hot in a universe that could have been otherwise. Each point of light represents a massive fusion reactor, converting matter into energy, pouring light and heat into the void. This is miraculous, really. This transformation of matter into energy, this creation of light from the marriage of hydrogen nuclei. We take it for granted because it's all we've ever known, but having imagined the opposite, perhaps we can see it fresh, with wonder renewed. Our sun, that ordinary yellow dwarf star that makes life on Earth possible, deserves a moment of appreciation. Tomorrow, when it rises, and for us, unlike in our imagined universe, sunrise brings warmth and light, perhaps you'll see it differently. Not just as the bright disk that marks the beginning of another day, but as a massive sphere of plasma held together by gravity, fusing 600 million tons of hydrogen into helium every second, creating the energy that drives our weather, our ecosystems, our very existence. The warmth you feel on your skin is the product of nuclear fusion, travelled across 93 million miles of vacuum to reach you. This is the everyday miracle we live with, the hot star that makes our world possible. The cold of space, which we spent so much time reimagining as warmth, also deserves renewed consideration. That cold isn't just absence, it's the canvas on which the hot stars paint their light. It's the darkness that makes the light visible, the emptiness that makes the fullness meaningful. The 2.7 Kelvin of the cosmic microwave background is the echo of our universe's beginning, the cooled remnant of the Big Bang carrying information about the first moments of everything. In that cold whisper, we can read the history of our cosmos, decode the story of how we came to be. But what if, just what if, somewhere in the vast multiverse that some physicists propose, there really is a universe where stars are cold and space is warm? What if the imagination game we've been playing tonight corresponds to an actual reality somewhere beyond our ability to observe? The beings in that universe, if they exist, might at this very moment be imagining a cosmos like ours, where stars burn hot and space spreads cold. They might find our universe as impossible and fascinating as we find theirs. Perhaps imagination is a kind of bridge between possible worlds, a way for consciousness to explore realities beyond the one it inhabits. The question we began with, what if stars were cold and space was burning hot, has taken us on a journey through physics and philosophy, through astronomy and meaning, through the concrete and the abstract. We've built imaginary telescopes and theorized about impossible planets. We've drifted through warm voids and orbited cold stars. We've considered how life and consciousness might arise under different cosmic conditions. And through it all, we've been engaged in one of the most fundamentally human activities, wondering, what if? This capacity for imagination, for counterfactual thinking, for exploring possibilities that don't exist, is perhaps one of the most remarkable products of our hot star universe. The same cosmic evolution that created stars and planets, and the complex chemistry of life also created brains capable of imagining other universes entirely. We are the universe becoming aware of itself, and part of that awareness includes the ability to imagine the universe being otherwise. In a very real sense, when we imagine other possible universes, the cosmos is imagining alternatives to itself. As you prepare for sleep tonight, you might carry with you some echo of the warm cosmos we've explored. Perhaps in your dreams you'll drift through those embassies, past cold stars that don't shine, through regions where temperature tells the story that light tells in our world. Or perhaps you'll dream of other impossibilities, other inversions of the familiar, other ways the universe might have been arranged. Dreams, after all, are where our minds freely explore impossibilities, unconstrained by the physics that governs our waking world. The journey we've taken together tonight has been long and strange, but it brings us back to where we started, in our familiar universe under our familiar stars, but perhaps with a renewed sense of wonder at the cosmic accident of our existence. We live in a universe where stars are hot and space is cold, where light travels through darkness, where life arose on at least one small planet orbiting an ordinary star in an ordinary galaxy. This is our reality, and having imagined it otherwise, perhaps we can appreciate it more deeply. Think about the generations of humans who have looked up at the night sky and wondered about their place in the cosmos. Ancient astronomers who mapped the movements of planets, medieval scholars who debated the nature of the celestial spheres, modern scientists who've decoded the nuclear processes in stars and the expansion of space itself. All of them were trying to understand the same universe we inhabit, the same cosmic rules that govern everything from the smallest quantum fluctuation to the largest galactic supercluster. And yet each generation has seen the universe differently, through the lens of their own knowledge and imagination. We stand now at a unique moment in cosmic history, when we understand enough about the universe to imagine it being fundamentally different, but still have so much to learn about why it is the way it is. We know about other planets orbiting other stars, but we don't know if life exists anywhere else. We know the universe is expanding, but we don't fully understand dark energy. We know the laws of physics, but we don't know why these laws and not others. We live in an age of both knowledge and mystery, understanding and wonder. The cold stars we imagine tonight will never exist. The warm space we drifted through is purely fictional, but the act of imagining them has been real. The wonder they've inspired has been genuine, and perhaps the peace they've brought as we contemplate them here in the quiet hours has been valuable. Sometimes the impossible is worth exploring, not because it could be real, but because it helps us see the real with fresh eyes, appreciate the familiar as if it were strange and wonderful, which, of course, it is. As we conclude our journey through this inverted cosmos, let's take a moment to appreciate the actual universe we inhabit. Look up at the stars if you can see them, or simply know they're there above the clouds. above the light pollution, continuing their nuclear burning as they have for billions of years. Feel the Earth beneath you, this small rocky planet that's just the right distance from its star, with just the right composition, rotating at just the right speed to create the conditions for life. You are made of star stuff, as Carl Sagan famously said. Atoms forged in the nuclear furnaces of dying stars, scattered through space, gathered together by gravity and chemistry into the pattern that is you. You exist at the intersection of the cosmic and the personal, the vast and the intimate. The same physical laws that govern the expansion of the universe govern the neurons firing in your brain as you process these words. The same carbon atoms that form the basis of your biology were once inside stars, will someday return to space, might eventually become part of new stars, new planets, new possibilities. You are temporary, but you're also eternal, a brief organization of matter and energy that's part of the eternal dance of the cosmos. The warm universe we imagine doesn't exist, but the capacity to imagine it does, and that capacity is just as remarkable as any physical phenomenon in the cosmos. Consciousness, imagination, wonder. These are products of our universe just as surely as stars and planets are. When you imagine impossible things, you're exercising a capability that, as far as we know, is rare in the universe, perhaps unique to Earth, though we hope not. You're doing something that cold stars could never do, that warm space could never accomplish. You're thinking about what might be, not just what is. Tomorrow, when you wake, the world will be the same as it was today. The sun will rise hot, space will remain cold, the laws of physics will continue to operate as they always have. But perhaps you'll carry with you some small echo of our journey, some lingering sense of the arbitrariness and wonder of it all. Perhaps you'll look at the ordinary world with eyes that remember having imagined it otherwise. Perhaps you'll find in the familiar rhythms of hot days and cool nights, bright stars and dark skies, a beauty that's enhanced by knowing it could have been completely different. The universe we've imagined tonight, where stars are cold and space is burning hot, has been our companion for these hours, our thought experiment, our meditation on the nature of existence. Now we release it back into the realm of imagination from which it came. It will continue to exist there, in the space of possibilities, in the realm of what if, waiting to be revisited whenever we want to remind ourselves that reality, however solid it seems, is just one arrangement among infinite possibilities. But for now, it's time to rest in the universe we actually inhabit, this cosmos of hot stars and cold space, of light and darkness, of the familiar wonders we call reality. The night continues its slow rotation toward dawn. The stars continue their fusion burning. The galaxies continue their expansion into the cold void. And you, small and temporary but also vast and eternal, continue your own journey through this one particular arrangement of matter and energy we call the universe. What if stars were cold and space was burning hot? We've explored that question for hours now, followed it through impossible physics and imaginary worlds, through philosophical implications and poetic possibilities. The answer, of course, is that they're not. Stars are hot, space is cold, and that's the reality we live in. But the journey of imagination has been real, the wonder has been genuine, and the peace of contemplating vast impossibilities has, I hope, prepared you for peaceful sleep. So rest now, under the cold stars of our actual universe, wrapped in the warmth of your own small corner of this cosmic reality. Let your mind release the inverted cosmos we've explored and settle back into the familiar rhythms of the world you know. Tomorrow the hot sun will rise, tonight the cold stars shine, and in between, in this quiet moment you exist, conscious, wondering, imagining, part of the universe's long contemplation of itself. The cosmos continues its patient unfolding, whether stars are hot or cold, whether space is dark or glowing. And you, for this brief moment in cosmic time, are here to witness it, to wonder at it, to imagine it otherwise, and to find in that imagination a doorway to deeper appreciation of what actually is. This is the gift of consciousness, the privilege of awareness, the miracle of being able to ask what if, in a universe that simply is. Sleep well, cosmic dreamer. Rest peacefully under the stars, whether you imagine them hot or cold. And remember, when you wake, that you live in a universe strange enough to produce beings capable of imagining it differently, wonderful enough to inspire endless questions, vast enough to contain all our dreams and impossibilities, and yet intimate enough to create this moment, this thought, this peaceful drift towards sleep. The cold stars above continue their ancient burning, the warm earth below continues its faithful rotation, and you, balanced between the cosmic and the personal, the vast and the intimate, the real and the imagined, continue your own journey through this one particular universe, carrying within you the capacity to imagine infinite others. What if stars were cold and space was burning hot? Now you know, or rather, now you've imagined knowing. And in that imagination, perhaps you found something valuable, not answers but better questions, not certainty but deeper wonder, not explanation but appreciation for the beautiful mystery of existence itself. The journey ends where it began, with you, here, now, in this universe, under these stars, preparing for sleep. But you return changed, carrying with you the memory of impossible worlds, the echo of cosmic warmth that doesn't exist, the shadow of cold stars that never were. And in that memory, that echo, that shadow, lies the seed of wonder that makes us human, that makes consciousness worthwhile, that makes the universe's contemplation of itself through us a beautiful and meaningful thing. Good night, traveller through imaginary cosmos. May your dreams be filled with wonders both possible and impossible, and may you wake tomorrow with eyes that see the familiar world as the miracle it has always been.